how is the summer school, the advanced session going on? I mean, I know the winter school was very intense in terms of how many things you saw within 5 days. How is it going so far for you guys? Still intense. But are you managing? Are you following along? I mean, I had a chance to look at the material from Erica a little bit, not so much, but I mean, it's not my area of expertise at all anyway.
It was definitely too much for a single lesson.
Yeah.
But I hope you managed to follow me because that was lots of things.
Yeah. And then I also saw Franco's, which speaks a little bit to what we will be doing today. And that was also quite intense. I hope you had a chance to follow that. And I think today, because of my health, but generally because of what we're going to do, I think we're going to slow down a little bit. And I think I remember last time in February, you welcomed this slowing down, at least on the Friday, the last day, and we still saw a lot of things, even without slowing down. So, I mean, I know the name of the lecture is called Machine Learning in Text Analysis, and machine learning is something extremely large as a concept, right? It includes a lot of things, and many of the things you've done in the winter school and the things you've done in the previous courses are all machine learning, basically. So all of these things are machine learning. So we don't have to do a very specific, dedicated class on machine learning for text analysis in general, but we will focus on something called text embeddings. Has anyone heard this term before in this room?
Actually, in the first day, we heard something like vectorizing the words.
Great. Vector is a great term to speak about embeddings. Embeddings are vectors. You didn't raise your hands, Andrea and Erica. I mean, like, you don't know about embeddings. Okay. So cool that you don't know about embeddings. You haven't heard about embeddings, but embeddings is an extremely useful and crucial tool when we do text analysis, okay? It can help you do a lot of things, especially when we are trying to figure out, when we're trying to work with meaning, semantic stuff in text. So we're going beyond simply counting words and simply seeing what words co-occur with others, like we normally do in text analysis, and we focus a little bit more on what meaning does a word carry comparative to another word, what meaning does a sentence carry comparative to another word, and how we can compare the meanings from different text sources, okay? So while our colleague is struggling with a microphone, we can do it in the break, don't worry. We can do it in the break. I really don't need it for now. Yeah, I don't need it for now. Yeah, okay. So you all got access to this, right? The slides and the workbook. So we will begin with a few slides, as we normally do. So in the morning session before lunch, I will introduce embeddings to the best way that I can. I think you will understand them pretty well after this. They are generally not the easiest to grasp thing from the get-go, but we will do our best, and I think you'll be fine. And then after lunch, we are going to look at how you can calculate embeddings in your texts and what you can do with those calculations. Can you visualize them? Can you compare? Can you interpret? And how we can apply them in social science. As with any other machine learning pipeline, just a small introduction about machine learning a bit. There are 2 slides here. I mean, we begin with text data. We extract some features from the data. Frequency of words, for example, is a feature. Then we run those features that we extracted through a model, and we're trying to do some prediction, and then we evaluate that prediction. That's basically the pipeline in any machine learning setting with regards to text. And the embeddings are not really different. Obviously, there is this step that is really not optional, which is the fact that you have to interpret the finding. So if you remember, we did BERT topic in winter, right? BERT topic was a way to cluster text in an unsupervised manner. So we let the data speak to us. We didn't choose, we could tweak some parameters, but in general, the model picked the things that mattered. So still, you had at the end to see the words of its topic, the major words of its topic, label it, and see if it's valid and if it's useful or not. So as with anything, when we are using machine learning in social science, you have to worry about interpreting, you have to worry about validating yourselves, and the human input is very crucial. So within this realm of machine learning approaches to text analysis, so we have the classical stuff, the supervised stuff, so where we supervise, and that's basically something like a regression. Everybody knows what a regression is, right? Or is anyone here that doesn't know what a regression is? Good. So in a regression in social science, we have a dependent variable that we're trying to predict and some independent variables that we think affect the dependent variable, right? So same thing in text analysis, but the dependent variable is a task. The dependent variable is a label, is a class. Let's say we had that problem of whether a piece of text is positive or negative, right? That's a label we are trying to predict. And in this case, it happens to be binary. It's either positive or negative. We would do a regression, and we would add all the features, all the independent variables there to try to predict that label, okay? So again, this is something we've been doing as social scientists for a long time, a regression, a logistic regression, something we know how to do more or less if you had some quantitative background. And this is the beginning of how people started working with machine learning for text analysis. So you use that to do, as we said, sentiment or stance or all that stuff. Thank you very much. Destekli. Then we have the unsupervised discovery, let's say, BERT topic, LDA, which is an earlier, STM, which is not here, but anyway, like this unsupervised way of getting meaning out of text. I'm skipping that on purpose. And then we have the transformer family of machine learning models. Oh, wow. Is this better? Wow. Maybe a little too loud. Okay. So, yeah, we have the transformer with fine-tuning or without, the BERT style models, BERT topic that we spoke about. And we have LLM-assisted coding. We talked about this a lot last time, where we used a proprietary model to annotate data automatically. I hope you remember that. And then I saw on Franco's material for 2 days ago that you also did some annotation with an open model, right? You asked an open weight model to do some annotation for you. That's another way to do machine learning for text analysis, but with large language models in that case. And you had 0 few shot annotation or fine tuning. And then you have active learning with human review, where you have a combination of unsupervised and supervised. Today, we will be talking about embeddings, okay? Embeddings and similarity, so whether two embeddings are similar or not. We're going to do a lot of things with embeddings today. I hope you're not going to be bored by embeddings, by hearing the word embeddings today, but you're going to hear it a lot. We're going to be talking about embeddings all day long. So, let's see what embeddings are. So, nobody has heard the word embeddings before, right? I mean, you said vector, I'm glad about that, but no one else, right? Maybe some of the new people have heard the word embeddings before? No. You have? Yeah. Okay. Would you care to guess what it is, or you?
The same. After we tokenize the text, we put the vectors, and it seemed like point in a graph, like the similar embeddings, same meaning words, like in a similar place. That's what I know.
Perfect. You basically described everything. We don't have to do this class. But you need to think of this in the following way. So basically, word embeddings are ways to represent text so that the machine can understand them, right? As we've done with all other steps previously, all of the things that you did today, you were taking text and you were transforming it into numbers that the machine can understand. Embeddings is yet another way of representing text in numerical manner. So it's numbers instead of letters and word structure. But they have a little bit more than that, and your colleague said some really crucial words there. So traditionally, when we do text as data, we normally use these features, but they are manually designed. We use word counts. How many times does a word appear in a text? We use term frequency, inverse document frequency. You remember TF-IDF? So we use the frequency of the word divided by how many documents it appears. So you have a collection of documents, and maybe in one document a word appears 1,000 times, but only in one document. And then there is another word that appears 1,000 times, but only once per document. Which of the two words is more important? I mean, it's a decision. Come again?
That's repeated many times in the one document.
So let's say you want to figure out if a word is important for your collection of documents, or if a word is not really important because it appears in every document, so it's not distinguishing, it has no distinguished meaning. So you would use term frequency, inverse document frequency. So you don't only count how many times a word appears in the entirety of your collection, but you also divide that by the percentage of documents that it appears as well. So you're controlling for that. Again, we're not going to worry about TF-IDF today. Just saying that it's there, and we've been doing that. Again, a very, very numerical way of representing text. We had dictionaries. We have topic proportions, as we saw with per topic, etc. We also used metadata. So for every text, every piece of text that we have in our document collection, we would have metadata about who the author was, when was it written, etc. And we would use that to figure out meaning and get to meaning. Embeddings are different because these features that we're going to talk about are learned from the data. We are not manufacturing them. We are not telling the model what these features should be. They are similar to per topic if you want to think about it. We are just feeding all the text to the model, and the model is telling us, based on its previous knowledge and its training, it's giving us these representations to the best of its capacity, which we will talk about, of course. So it's an unsupervised approach, obviously. So again, the number one thing I want you to remember is that word embeddings are word representations. Just another way of representing words. Normally, these embeddings come from models that have been trained on enormous text data. The early first major generation was Word2Vec, Glow, and FastText. FastText was from Facebook. Word2Vec was the thing that revolutionized the field, and everybody started using embeddings. But you should imagine that we take these models, we train them on huge corpora of text, so books, for example, thousands of books, and the models are capable of understanding concepts and meaning a bit better. So I know this sounds a bit repetitive, similar to what large language models are, but we are not in that territory now. We're doing something different, and I'm gonna speak to you about that. In any case, these models, because of this training, they are able to capture these semantic relationships between words. In the end, what we get is that words or pieces of text, but words, let's talk about words for now, with similar meaning have similar representation. So they have a similar embedding. So we assign a representation to the text, and if we have two texts that are similar, they should have similar representations as well. And obviously the other way around, right? If the texts are not similar, they should have different embeddings as well. A super common example is this king, man, queen, woman example. So as your colleague said, remember these representations that we're talking about, these embeddings are numbers, are vectors actually, that are multidimensional. What does multidimensional means? It means that this vector has more than one values in it. And as many values in the vector, separated by a comma, this many dimensions we have. So if we have a 2D plot like this one dimension and the other dimension, so these are 2D vectors right now. So if we were to create two-dimensional embeddings for these 4 words in our corpus, in our example, we would get something like this. So for one dimension, the word king has 1.5, and for the other dimension, it has 3. This is a vector. This is the embedding, the two-dimensional embedding for the word king. Then the same for queen, same for man, same for woman. So these spots here are placed in this two-dimensional space. This is a two-dimensional space, right? It's a plane. Not a plane? a plane. Classic joke. Yeah. So the word king and the word queen are relatively similar, right? The word man and the word woman carry some, comparatively to king and queen, maybe a bit more meaning. So your colleague said something, what was your name, sorry? Yahya? Okay, I'll try to pronounce that correctly and not butcher it. So Yahya said that the importance of these embeddings is that it places these dots in a way so that words that are similar in meaning fall closer together in this space, okay? So if you have two words that are similar, and we're talking about words now, but we can extend this to texts, two words that are very similar should be closer in this embedding space than two words that are not similar, okay? So their vectors should be closer. Is this making sense? Any question up to this point?
Not yet.
Good. I'm going slow for 2 reasons. One, because I cannot speak very fastly today. And 2, because I think this is really crucial that you get and that we move on with this very, very well grounded. So as I said, this is an embedding. This is a word representation. This is what we will be doing today.
Can I ask a very stupid question?
There are no stupid questions. The classic mantra. Yeah.
What does the x and y axis represent exactly?
So in this case, nothing. Let's not worry about labeling this. So the model, we asked it for 2 dimensions, and it provided 2 numbers for each word based on its data. But it picks what matters. It picks what sort of thing is inside king, the 2 dimensions inside king that should be placed here. I'm gonna speak a little bit more about the dimension than the dimensionality, but so bear with me. If it's still not clear in the next slide, you can ask again, okay? So the classic example is that given the fact that these are numbers, a vector is a list of numbers basically. We can do math with it. So we can subtract 2 vectors, we can add 2 vectors, we can divide, multiply vectors, okay? So the cool thing that happens here with these embeddings is that you got the embedding of king, so the representation for the word king, and you can subtract from that the embedding, the meaning, the representation of the word man. Whatever the word man carries, you subtract it from king. Whatever the meaning of man is, you subtract it from king. And you add to that the embedding of woman, and whatever that represents, whatever that holds inside. And you should get, at the end, can you guess?
Queen.
Good. Yay. I mean, it was here. Yeah. So if it works well, and we will try to test this later on, you will be doing this. We get the embedding of king, we subtract the embedding of man, we add the embedding of woman, we should get roughly close to the embedding of queen, to this value that we have here. Don't try to do this, these are random numbers here. Maybe it works, I'm not sure. So we were at king, we took that out, so we moved somewhere here, and we added woman, and then we moved somewhere here in the space. So now we are closer to queen, right? This is the magic of embeddings. This is why embeddings can be really cool.
May I ask something?
Of course.
I'm just thinking, like, LLMs are they using word embedding? Because I'm thinking what we call hallucination might be a raw mathematical representation of words.
Yeah.
And
This is a-
thinking, is it the case?
This is a great question. Really, really good question. So LLMs are very different, but also not super different than this case here. So LLMs focus on generating tokens. So it has a list of words, and by looking at probabilities, auto-regressively, like Franco told you 2 days ago, it tries to predict the next token, right? So LLMs are about predicting what the next token is what the best next token is. In this case, we're asking the model to provide representations for text that it hasn't seen before. So there are two different tasks. So on the one hand, we are asking the model to tell us something based on what it knows, but also on this new collection of text, and tell us something about the entire corpora at this particular moment. In an LLM, we are asking a completely different task. So they're not really comparable. They are two different things, but I mean, under the hood, they are both using numerical representation just in a different way. They are still using embeddings as well, but in a much different way and in their training stages, not so much in the generation phase, while you work with them.
But I'm just thinking, sometimes we see from these LLMs some kind of weird words.
Mm-hmm.
Maybe they are making a mathematical representation and they're finding something different, maybe meaningful mathematically, but not meaningful semantically.
Exactly. No, I mean, again, despite the fact that these are two different technologies doing things differently, I mean, the underlying structure is that we take something that has incredible meaning, language, has incredible meaning for our lives, the way we exist, and we are trying to put all that into math. Obviously, that reduces the complexity of language to something more manageable in our minds and the computer's capacity as well. So obviously that involves that step of mistakes happening, right? And misclassification, misunderstanding of text, and comparisons that go wrong. So once again, it's extremely crucial, as when you're working with an LLM that hallucinates, to be sure that when you get a vector, you check if that vector makes sense or not. But later on, I mean, now we're working with 2 dimensions only, x and y. Later on, you will see that we will have vectors that are 384 dimensions long. That's not even our brain is not even able to comprehend, so it's not also easy to check what a vector is. But you can check what happens when you compare 2 vectors and if 2 texts are similar. So we will do that. But yeah, have I answered your question?
Yeah, definitely.
So with embeddings, instead of saying this document contains the word immigration 4 times, we move to something like this document occupies this location in this semantic space, this geographical space, okay? Geometric space. And that location is produced by a machine learning model, so this embedding model. So similar to the king-queen example, which is this, these models can understand verb tense examples as well. So the embedding for walking is as far from walked, the embedding of walked, as is the embedding of swimming for swam. Okay? So if you were to see the embedding of these two words, you would see that the distance in them should be similar. So if you were to calculate the distance between the two, you should be getting the same value. Same with cities and capitals. So China to Beijing should be the same as Russia to Moscow, okay? And you can go way, way beyond that. You can go to much more meaningful semantically stuff, much more social sciencey stuff, as we will see later. Then from word embeddings, we move to text/document embeddings. So the same way you can ask the machine to give you an embedding for a word, you can ask it to give you an embedding for an entire piece of text. It could be a sentence. It could also be a paragraph. It could be an entire document, a speech in parliament, a tweet, whatever you want. You can have it return an embedding. Before I move on, just very briefly, so I said that these are two-dimensional. Let's think about the multidimensionality a little bit more. So imagine I'm Yani, right? And I want to numerically represent me with a vector. So I put a vector on top of my hand, so whenever I walk, I have like a vector here that represents me. So what would it be? So let's say the first dimension is the continent in which I was born. One's for North America, 2 is for South America, 3 is for Europe, 4 is for Africa, etc., right? So I'm from Europe, I get a 3 in the first dimension. Then comma, second dimension, my age, I'm 35, so we put 35 there. Third dimension, something else about me, if I'm a male or female. Fourth dimension, if I have a degree, if I have studied. We do this in social sciences, in surveys. We collect this information in surveys and we try to predict whether a person will vote for a certain party or not, right? So imagine the same thing here, but for text. So we assign, so in the end I have a vector with all these values here. You have a vector with your own values. You have a vector with your own values. And imagine we have 384, this is a common number, that's why I'm saying it, way more than 2 dimensions. We are multidimensional persons, right? We have a lot defining who we are, what our background is. So the more dimensions we have in this vector, the more meaning this vector carries, and the more it can tell us about the person and the text. So you should think of embeddings like this. So they have numbers in them, but each number has, in the mind of the model, every dimension in the mind of the model carries some meaning that is important for that word and that piece of text within the context of its knowledge and the document collection that you have in that particular instance, okay? Does that make sense? So from now on, we will not be seeing two-dimensional embeddings anymore. We will be seeing 384 mostly dimension long vectors. So imagine a vector with 384 numerical values separated by a comma. Those are the embeddings we're going to be working on. And if you try to put those on a plane, you can't. On a plane, not a plane again. So this is a two-dimensional geometrical map. If we added a third dimension, we can still imagine it's 3D. We just add an axis going this way, right? That's a 3D. That would be a 3D space. But if we were to add the fourth number, already our brain cannot comprehend 4 dimensions, right? Imagine 384 Like it's something we cannot comprehend, we cannot do, we cannot visually represent. So we let the math do the work in comparing these vectors, and we try to not think about visualizing that anymore. If we want to visualize, we will show you what we do. We reduce those 384 to the 2 or 3 most important ones, and we visualize those ones in 3D or 2D plots. But we will do that later. Is it clear right now? I mean, you had a question. Is it answered?
It is answered.
Excellent. Any other questions so far? Good. So let's move now to documents. Imagine we have these two, again, a very classic example. We have these two documents. Can you see also from there?
Yeah.
I'm sorry I'm standing in front of you, but you let me know, okay? Also, the slides are in the Google Drive, so okay, good. So document 1, Obama speaks to the media in Illinois. And document 2, the president greets the press in Chicago. How similar do you think these two sentences are from 0 to 1?
0.7.
Okay. Any other opinions?
We're guessing?
Yeah. Well, basically you can say, is this similar or not similar? Binary task, binary classification. Okay. Anybody thinks that it's not similar?
I feel it's not.
They are not similar. Okay, what do you think that?
Greeting and speaking can be different.
Sure.
So that's how
One more friendly and the other one more, okay. But if you were to read these two sentences in two different media outlets, would you say that they are talking about different things?
They're representing it in different ways.
Yes.
Okay. But so I open a newspaper in Greece and I read this sentence, and you open a newspaper here and you read this sentence.
Okay.
Are we learning something different about what happened?
Yeah, because I might think it all happened on different occasions.
Yeah, also taken different places.
Yes.
Different places. Okay, so maybe that's the point. So
Yani,
yeah. So
the context, I think, defines who is the president. There it's clear it's
Good.
Obama, and here it's
so
be a Turkish president as well.
right. That's a good point. Especially if you're reading a Turkish newspaper. So maybe that example was not great. So by the way, Chicago is the capital of Illinois. Illinois is a state in the United States, right? So if the president greets the press in Chicago, I guess it's the United States president speaking in Chicago, most likely. It could be, if you're reading it in Turkey, I guess it could be
Context.
Erdogan. That's really important. You're right. But let's say we are reading two newspapers in the States.
Okay.
I would argue that these are extremely similar sentences. So I'm closer to the 0.7 value. But I agree that they can be different. Let's think about text analysis in the old traditional terms of counting words. These two texts basically have they have a few similar words. So the word in and the word the is there. But if you remember, these are stop words. So we would remove them anyway. So out of the words that matter, they share no words. So with the old text analysis technique, these two documents are completely different. They are not speaking about the same thing. Would you say that they are completely different?
Not completely.
Okay. Would you say that they are completely different?
No.
Okay.
With the removal of the stopways or what?
Yeah.
No.
Okay. So I also agree. I don't think they are definitely we are not on the completely different side. So if we were to do text analysis in the old way, these would be two completely different documents. However, if we use word embeddings and we place these words and their embeddings in a two-dimensional space, we would see actually that Obama is close to president. The embedding of the word Obama is close to the embedding of the word president. Similarly, the word speaks is close to the word greets. I understand that they carry different meaning. One is an action of speaking, the other an action of maybe just shaking hands. You are 100% right. But in terms of embeddings, the word greets and speaks are much closer than greets and fights, or greets and struggles, right?
Yes.
Also, Chicago and Illinois are close because, as I said, is the capital of the state. Press and media, we all agree, right, that these embeddings are very similar. So if instead of comparing words, you compared embeddings of a text, you would get a much better way of comparing semantically two texts and see if they are similar and if they're speaking about the same thing. Can you see how powerful this can be? So imagine you want to say you have a large collection of texts and you want to focus only on those texts that are about the economic crisis of 2009. Imagine you want to work on texts that are only about the World Cup happening right now in North America, right? If you wanted to extract those sentences, you could check them manually, one by one, obviously. But in a context of having thousands of texts, that's obviously not possible. But you could use embeddings and see if they are close to the embedding of, let's say you write a sentence about the World Cup. So World Cup, comma, some other words that are important for your case, and you define the topic. And you calculate an embedding for that topic that you have. Now you have a representation for that topic that the model decides what should be put on top of it, right? So we get an embedding for that sentence, that thing that you defined. Now we are asking the model to do this embedding calculation for all the sentences in our documents. And then we ask it to give us back only those that are similar to the first embedding. We will do this. So this is a way of also classifying text, seeing if a text is about sports or not, if it is about the topic you want to talk about or not, and we will see how this works. Yes?
It's a small question, and it's actually based on something that Arzu Hoca brought up. So
of course.
Citation.
So it's here, credit to her.
We were discussing, on day one, Giovanni Hoca had introduced the Little Prince text for
Right.
the BERT transformer model.
Right.
And there was this problem because the BERT model read the rows, so the time wasted for your rows is what makes it so important as rise rows.
The past tense of rows.
Yes.
Yeah.
So would this embedding actually take care of this problem, or do we still see those?
So that's a great point. So the old embedding models, so the ones that I showed you, were not good at picking this up. So rows and rows would be the exact same word for it, unfortunately. However, the updated, so LLMs can distinguish between the two based on attention and the attention mechanism that I think you spoke about again in this class a little bit. The idea that the model can within a sentence, within a context of a document and a sentence, can figure out what words matter and give meaning to the word rose, so that it is a rose or it is the past tense of the word, the verb rise. So modern models have the capacity to figure this out. Also embedding models have the capacity to do that as well, okay? So it's not something that should worry you. But still, there are many other sources of error that are out there, and we're gonna talk about them. But that is not one you should worry too much about, yeah. Any other question?
Yeah, I have a question.
Yes.
Well, if the embedding is trained for figuring out the public figures, like Obama, for example.
So filtering out public figures, in my eyes, is a pre-processing step. It's not an embedding step, but you could be using embeddings to do that. So you could have a model calculating embeddings for you, and you could define the topic that says public figures, presidents, prime ministers, etc. So you write your own, you define your own topic, for example. We will do this, so you can try actually. And then calculate an embedding for that. And then in the text, in the other texts, you compare that embedding with the embeddings of the text. So the embeddings that are similar, the ones that you're going to get back, are going to be those that contain public figures in them, most likely. But we can try this. This is a good idea. But what are you thinking, like filtering out public figures?
I was saying, like, if the embeddings have the vectors for the public figures, or no, because here in this example, there is Obama. That's why I'm asking.
So we have. So you're asking if the model. No, yeah. Sorry. So I misunderstood the question. So you are asking if they calculate embeddings for public figures as well. So are you aware of what entity extraction is? So in text analysis, one really useful tool we have is identifying names of organizations in text, or places in text, or figures, people in text. Sometimes we want to treat those a little bit differently, and we do that with something called entity extraction. Modern day text analysis with LLMs does not need that, because it has seen so many text that knows where Chicago is and where Illinois is, knows who Obama is, knows who the president currently is of any given, well, most countries. So there's no need to actively do entity extraction. So yes, to answer your question, the model can easily calculate an embedding for the person. The problem is, if it hasn't seen, and that's where the problems sort of start. If it hasn't seen that public figure too much in the data, the embedding that is going to place on top of, let's say, Yani Kartalis, like I'm really not a public figure, right? So it's going to place an embedding on me on the word Yani Kartalis. Let's say it's a bigram, it's one thing, based on what it has read. So if I go to an LLM now and say who is Yani Kartalis, maybe on Google, like the Yadesa stuff is there, my position at the University of Copenhagen is there, and it can find some references about me and it will tell you something. But an embedding model doesn't have this interaction with search engines currently. So it's based on what it has read in the previous texts about me. So a person that is maybe a public figure but is a smaller public figure and is not Erdogan or Obama will get an embedding on top of it that is potentially less meaningful and less accurate. So yes, 100% to your question, we get embeddings for public figures, not like previous text analysis. So public figures, places, names, company names, they get their embeddings. It's just that if the data is not enough, that embedding can be a little bit less accurate, and the placement in the geometric space can be less accurate, okay? Does that make sense?
Yeah.
Any other question? So we can calculate embeddings on any kind of data that we have, way beyond text. So we can calculate embeddings on images. So there are embedding models that again digest images and assign a vector. I'm using this with my hands because normally a vector has a bracket, square bracket on the two sides, okay? That's why I'm doing this. So whenever I do this, you should think of embeddings, okay? For today, for today at least. So we have an image, an embedding model can assign a vector to it, an embedding to it, a word representation to it. We have documents, as we said, but audio files as well. There are audio embedding models that assign embeddings to an audio file. So you have two audio files, you get one embedding for the one embedding for the other, and you compare the two, and you can see which audio files are more similar semantically, okay? Obviously, if you are working with sound, how many of you were present in the sound analysis seminar? Who attended the online one? Okay. You were there?
I watched it on YouTube.
Really? Twice?
Yes.
Was it that good?
Yes.
Well, excellent. I'm glad. Okay, that's a compliment I'm taking very well. Thank you. So So if you're working with an audio file, obviously the embedding of the audio file carries meaning about the digital signal that is audio, right? And not the thing that is being said inside. So an embedding about an audio file is telling us things about the voice of the person speaking, the pitch of the person speaking, if you remember all these characteristics of audio, and not the content of the speaker, right? Not what they are saying. If you care about the content of the person speaking and what they are saying, you need to extract the text with transcription and work on the text as a regular text analysis. Also with images, when we do embeddings of images, we're doing embeddings of how the pixels are placed. Maybe image analysis is another course we need to do, but that's later on. Anyway, you can calculate embeddings for all kinds of files, okay? And then the embedding model will give you vectors multidimensionally, and if you had 3 only, you could plot them 3-dimensionally in a plane. So it's not a plane anymore, right? So just to give you an example, so this is from a project of mine about a year ago about media analysis in Greece. So this is about 2 million article titles and their embeddings in a 3D dimensional space. So I asked an embedding model to calculate embeddings for 2 million articles in Greece, and I placed them on this map to see what comes together. And I also calculate whether an article is pro-government, anti-government, or gray, unsure. So the green values here are articles, titles that speak positively about the government, and the red ones are articles that speak negatively about the government in some way or another. And also the way they are placed is the embedding that the model decided to place on them. So we have clusters of meaning or topic or whatever they are talking about, and also whether they are more positive or more negative, okay? And this thing now, like, I don't know if you can see this so well. So there is a cluster here that is like this thing here that is relatively unsure, so not really pro, not really anti. And okay, I know you cannot read Greek, so this is the title of the article, but this is only about forest fires. So in the forest fires, not forest, fires in general, well, actually, I would expect that they would be speaking more anti-government. But anyway, maybe this is a case of just reporting the fire taking place, and they are not, they don't carry too much anti or pro-government stance here, okay? Let's go to somewhere where there is a lot of green or something. So first of all, so this is a green cluster here, right? This thing here. Yeah, it's mostly about economics in this case. And it's about how good the Greek economy is recovering and how great of a job the Greek government is doing, blah, blah, blah. Right?
The clusters they are pointing out the topics in the cluster. When we say cluster, what should we include?
When I say cluster is what I visually see clustering together. So I didn't ask for any clusters here. This is a different thing we're going to do later today. But when I say cluster is what I see here as a cluster, right? So when I come on your side here, I mean, these are article titles clearly outside the way of others, right? So I'm saying this is a cluster, but it's not mathematically or something else. It's a cluster because the embeddings of those titles happen to fall closely in this 3-dimensional space. That's why.
They are close, like semantically.
Yeah, but when I went through the titles, they are all about fires, right? So again, this is a cluster here, right? So an article title here, an article title here is much closer than an article title here. So it speaks about something that is much closer here than there. That's the idea of embeddings. We place them in a space, three-dimensional in this case, so that things that happen to be closer, they are closer semantically as well. What makes them semantically closer is the tricky part. In this case, because we have a corpus of 2 million article titles from news, what makes something closer to each other is whether they are talking about the same topic thing. Obama spoke to the press in Illinois. The president greeted the press in Chicago. So these would have really close embeddings in this space. They would be very close. But what I wanted to do for this project was to see if when they were talking about the same thing, how they were talking about it. That's a relatively different step. You see the difference, right? So I don't care about if you are talking about the Obama going to the press. Okay, I care about that because I want to compare you, but I want to figure out if you speak, when you talk about this topic, do you speak more pro-government or more anti-government in this case? You can do this in many other ways. So when we have wildfires, do the media attack the government or protect the government? When the media speak about femicides, do they portray women as victims or as if they I'm trying to say this the right way, but are they portraying them as victims or as they deserved it or something like that, right? So when we're talking about, so you see the point, right? So it's not about whether you speak about the same thing. I care about whether you're talking about it in the same way. So potentially with embeddings, you need to figure out what this vector is telling us, what meaning is carried in these dimensions. Okay, I care about whether they're talking about the same thing, but there needs to be something in these 384 dimensions that is also telling me about how you speak. So when I compare the distance, that should be factored in there. And sometimes what you need is two steps. One, you do an embedding step for bringing the topic, the sentences, and the documents about one topic into place. And then you do another embedding step that calculates embeddings within that area. So it's about how they speak. Or you incorporate metadata, or you calculate sentiment again, or you do another extra step about meaning, okay? Cool.
Did you do this with large language model or?
This plot?
Yeah.
It's extremely simple. Huh?
Not just the plot, like embeddings.
You will do this today. Well, not this 3D map exactly. Well, actually, you will do a 3D map today, just not this one. Not this HTML moving around one, but it's really easy. And if you reach that point at the end of the class and you build your 3D map, it's extremely easy to go from that to this step of moving around an HTML. But you will do this today, okay?
Sorry, I have a question.
Of course.
Can we assign meaning to the whole cluster, not only the embedded points?
Excellent question. So let's say you have, correct me if I'm wrong, I'm just gonna say the question one more time. So let's say you have, in my example of 2 million articles, we have in newspapers, we have section names, right? This is international, this is national, this is sports, etc. So you have two ways of getting embeddings for the section, right? How does the national section of a newspaper represent stuff? How does the international section? So you have two ways of doing that. Either you calculate an embedding for every article separately, and then because they are numbers, you can get a mean score. You can get a mean embedding for the entire section. So I get all the embeddings of one section and get the mean value of all those. So this new embedding now that I have represents the entire collection numerically. Whether it's true or not that I somehow managed to put all this meaning into one vector needs to be tested, needs to be verified. I'm looking at you because it brings me back to whether something numerical can capture this. The other approach is to put all the text together and get an embedding for the entire text. But that's less productive in my eyes. The other one is a bit better. So the approach generally is to mean. Another thing I did for this project was I got the average embedding for each newspaper that I had. So all the texts, all the titles of one newspaper put together, all the embeddings meaned together and get one vector, all the embeddings mean together and get a vector for the other newspaper, and so on and so forth. And we will do something like that as well. We will get mean vectors as well. Does that make sense?
Is it like taking the average of each section? Let's say in the international section, you're taking the average of whether it is pro-government or anti-government. Is it something like that?
Pro and anti is something I did for this project, right? Don't think about it. It's just, so imagine if all the dots here were gray. Don't think about the color here. The color is an added layer that we added, has nothing to do with embeddings. I calculated pro and anti-government stance with an LLM. So I asked an LLM, like we did, to annotate, is this pro or anti-government? So in my data frame, where every row is one article title, there is a column with the text, the article title, some metadata about dates, etc. There is a new column with the embedding, and then another column with the pro-anti-government stance. So it's a completely separate thing from embedding. So now we're focusing on where they are put in this space. That's the embedding, okay?
So the second stage was not embedding?
No. So the pro-anti-government stance has nothing to do with embedding. Sorry if that was confusing. It's another thing. So it could be whatever you are interested in. In this case, I was interested in whether clustered things are more green or more red. I wanted to see if there were topics, clusters of topics, for which the newspapers were speaking more pro or anti-government. Maybe they are more allowed to be anti-government in certain areas versus others. That's what I was trying to find out. So, just to answer your question again, to go back to what you said, the embeddings are calculated with an embedding model. The embedding model, the only job it has is to get you a vector for whatever you feed it in. You can feed a word, you can feed a sentence, you can feed a paragraph, you can feed a collection of documents all together, right? Whatever you feed, it will get you an embedding based on the knowledge that it has. To the best of its capacity, try to put all the information that is contained in this text in 384 dimensions, in 384 numbers. Each of these numbers carries some meaning about what is in there. If, for example, this text is a little bit about the World Cup, it gets a value there about the World Cup. If it's a little bit positive in sentiment, it gets another value that represents positive there. If it's a little bit pro-government, it gets another third label. 384 dimensions that the model decides carries meaning for this particular piece of text. And then boom, you put it in a geometric space. Any other question? Yes?
Where does this 384 dimensions come? Who decides it?
The model.
Is it always fixed numbers?
It can be more and it can be less. For our purposes in working with Google Colab on the CPU only, the free version that we're all using here, we're going to work with 384. But it can be much more and it can be less. But that's a very common spot. There are scientific, in terms of computer science, I don't know how you select how many dimensions are there, if there are metrics you use to get.
A good rule of thumb that everyone is
Okay.
But for like the more dimension you put in, the more complex the analysis you're doing becomes. So you could expect that a lot of dimension would lead to a better result, in the sense that the points in the space, in this geometrical space, are more placed accurately, but that can also backfire. The more dimension you have, the harder it is to compute distances between these kind of multi-dimensional spaces. So I don't know if this confuses you even more. There is no strict rule. It's just you gotta have faith in the computer.
You gotta have faith in the computer, and also you can also validate something, right? To the best of your capacity, because we're talking about tons of articles. So why is 384 common for maybe this LLM I'm using gets 384, this embedding model?
The guys in the Word to Deck paper, they used that, and so everyone went along with it.
Okay. Good. Yeah, that also sounds like a valid strategy. Yeah. The idea is that, let's focus on something Andrea said. So imagine the embedding about me, about Yani. So I'm a complex person, right? I have a lot of things that make me who I am. If we just say Yani is 35 from Greece, male, okay, you get an idea about me, but that doesn't carry all the meaning that you need about me to figure out who I am and how to talk to me, right? Maybe that's enough, but the more dimensions you have, the more you know about me. So the better, the more accurate picture you have of me. So think about the same in text. So the more accurate, as Andrea said, the placement of that dot is going to be in this in the geometric space, which is extremely multidimensional. We cannot even imagine it. So more dimensions means more accurate placement. But how these dimensions are picked relies entirely on the amount of data and text that the model has seen. So it's completely data-driven, data-generated. So we basically don't have too much to say on that. What it picks, why it picks what it picks. Is there any other question right now? Okay, so I think we should take a break of about 10 minutes. And we start again around 20 past. Is that okay? Okay, good. So I want to speak a little bit more about this plot just once more. So the location of its dot has nothing to do with its color, okay? The embeddings only decided the location in this plot, so where it stands. And that has to do with its meaning semantically, what it is about, okay? The color of the dot is just an added layer. I'm sorry I'm repeating this, but I think it's crucial here. Anti, pro, and unsure government stance has nothing to do with embeddings in this case, okay? So I'm just repeating it once more. This is an added layer that I added here. So having said that, because these are in this case, 2 million article titles that speak about a multitude of topics and things, the defining characteristic that places them in this geometric space is what they talk about, just because of how many things they could be talking about, right? So whether they are close, it's not so much how they speak about the government in this case, or how they talk about the topic, but it's rather the topic itself they talk about. So articles that speak about the economy are in one sector, in cluster. Within that cluster, articles that speak about budget stuff is in one thing. Articles that speak about international economics are about one thing. Another cluster could be stock markets, etc., right? So the topic is what brings things together here, because these are 2 million article titles. If I wanted to see more the how they talk about something aspect and bring that dimension more to the front, what I could do is filter down the articles that I have to make them about a specific topic that I'm interested in. Let's say I was only interested about budget articles, articles about the budget. I can pre-filter and feed to the model only those articles that are about the budget, and then place those embeddings into a map and see. Then the location about them is no longer about what they're talking about. They are all talking about the budget, but their locations is more about some other aspect. Ideally, hopefully, what I'm looking for is how they speak about the budget. Okay? So let's say we have two documents. We used this example before and I liked it during the break. So let's say two documents. One says budget well spent, and the other sentence says budget wasted. Okay? If I have 2 million articles, the defining characteristic of these two about whether they're placed together or not is the word budget. Like what they talk about is more important. If I only feed articles that are about the budget though, then the importance for the embedding model will move towards the wasted and well spent, okay? So filtering and feeding a sub collection of articles is really important, okay? It can be really important. And you can do filtering in many ways, as simple as keyword. So you can have a keyword list, and if that keyword list is in the article, then you filter that article in and you include it. But we can think of other ways like per topic, etc. But think about this step as well, right? So here I'm just putting in together 2 million articles about an incredible variety of topics. So when I plot all of them here, how they are placed is more about what they talk about. Does that make sense? I think this is pretty key to understand here. If I took only the economic section articles, only the wildfire articles, this plot would look different. And where the articles were placed, it's as if it would be zoomed in a bit more. And where they are placed is going to be more about how they talk about this topic.
So,
Yes.
for example, if budget, talking about budget is one of the 384 dimensions, and if we filter it, then you're making this crystals embeddings to be 383.
No, that's a good thought, but unfortunately no. You would still get 384 dimensions by default because this is the model we're using. But it's not really about removing dimensions. It's more about comparing apples to apples versus comparing apples to all the fruits that are out there.
But one of the dimensions has like value 1, the highest, so they're close.
First of all, I'm glad because it means you're paying attention. So yeah, let's say it does have 1 in one dimension, which is about whether this is about budget or not, economics or not, or something like that. Then another could be about what kind of section in economics it is. We are labeling this, but it's not the model that is doing. The model is just giving you numbers. So we are just playing around here with this concept, right? This is not how it happens. So it could be that one dimension could be about this, and the other dimension could be about econ, etc. If you filter the articles about budget, you're not going to get a smaller vector. You're still getting the big thing. It's just that when you compare these two now, you are in a zoomed in section here. So I'm not. So let's say I care about this cluster here. If I remove everything else and focus only on this cluster because those are the articles that I want, then their relative positions to the other are more about how they speak about the topic versus what they talk about. If I compare this distance from here to here, obviously it's going to be a larger distance than here to here. So my distances here are about how far they are. They are about what they talk about.
Okay, but so there are 2 points. They are all about budget or same topic.
Not in this case.
Okay, 5.
But let's say we do it about budget, yeah.
So their dimensions, their distance is relative to each other or everything in the data, like training data. So if I, for example, an particular article about both budget and fire, and I filter two data sets about budget and fire, but that same article have the same value in both.
Yes,
two different. Okay.
it's one embedding for everything. It doesn't matter. So the filtering is not going to give us different embeddings. Okay? Whether I give the model a collection of documents that have been filtered or give the model all the documents at the same time, they will get the same exact embedding. Okay? So it doesn't make a difference. What makes a difference is the relative distances now between the vectors. In the first, I'm comparing this stuff with this with this. So these are super long distances, and they are consuming the tiny distances here that in my case are more important because I care about how they talk about something, not what they talk about. But because I'm comparing these long distances, which are about what they're talking about, I'm losing the smaller part. So by filtering, you focus more, the distances are going to be more about how, is what I'm saying. So just think about this thing that if I put all the data together, then the distances are about something. If I focus on filtered chunks of the data, then the distances are about something else. I hope in this case that one is about what and the other is about how, but that's not guaranteed. But the decision matters, the choice matters that you make. Is that clear? Sure?
Well, I have a question.
Of course.
Regarding similar applications, especially with the social media. Let's say, for example, as you said, someone wrote an article with the title, the budget is well spent, but he's being sarcastic.
Mm-hmm.
Can the embedding model like figure out such meaning, or is it?
So embedding models are very advanced, and like LLMs, have much better capacity to figure out sarcasm. But in a scenario as short as this, I think any model, I mean, you are not even sure if it's sarcastic or not. You need context. Yeah. You need to know who this person is, what they talk about normally, or if they added another picture saying, like maybe there was a picture saying that budget, I don't know, something bad about the budget anyway, and it's clearly in contradiction with budget well spent, because the person is making an irony, a sarcasm there. But yeah, it's a notorious hard problem for any model, so it's hard for embedding models as well, especially that particular one, the way you're mentioning. But generally, models are generally becoming capable of figuring out sarcasm. But it is a problematic for sure. Cool. With that out of the way, let's wrap up the slides. So with embeddings, you can do a series of things, including similarity search, as we said. What is similar to what? You can do clustering and classification. Is this about a topic? Is this about this particular thing that I'm interested in or not? This is how search engines do information retrieval. So the moment you type on Google something and you hit enter, that sentence that you gave is turned into an embedding. So an embedding model behind it is making it an embedding, assigning it an embedding. It goes to its database with existing embeddings, and it compares to all of them. Well, not exactly to all of them, and it gives you back the results that are closer to this embedding, as close as possible to this embedding. Okay, that's how search engines work right nowadays. Before they would work in a different way with other algorithms that were slower, etc. But now that's how search engines work. That's how recommendation systems work. Anybody here uses streaming services to watch content online, like Netflix, stuff like that? So when you're on Netflix, it gives you recommendations, right? It says, I think you want to watch this and this and this. I mean, it does this because it has given you an embedding as a user based on what you've seen, what you've started watching and stopped. These are all dimensions that are in there based on the model that they are using, and it's proprietary, and we don't know what's happening behind the scenes. And then based on that embedding you created, it has also calculated embeddings for the series that it has. For every series in their database, they have a separate embedding. And then they just compare your user embedding with the embedding of every series. And those that are similar are being pushed to you. Isn't that cool? And obviously visualizations, which we've seen and we're gonna do as well, and they can carry meaning. I mean, this 3D map that we showed carries meaning, but it also convolutes things a lot. And it's not super clear what I'm getting out of this just by putting things together. I mean, and obviously you cannot have a 3D map on a paper, right? It's kind of hard to put a 3D map on a 2D paper. So for a presentation, it's cool, but what can I tell a reviewer about my paper, right? But yeah. In the social science in particular, these embeddings, using embeddings allows us to compare text more about meaning, and the exact words are not that important, and we said this. And you can do a couple of things. You can do semantic search in very large text collections. So an embedding model like the one we are going to use is very good, very high performant, but also very efficient. So we're going to see that in the small data set we're working with, but it's still 3,000 articles data set that we're going to work with. It calculates embeddings within a minute. So it's still extremely efficient and only CPU based. Like if you had GPU acceleration, if you had access to GPU acceleration by paying a better Colab Pro account or something, you can get it that extremely faster. So if you have a large data set, you can very quickly with embeddings filter out, do certain semantic search stuff, and filter out documents that are not important and not relevant for you. That's extremely crucial if you're working with large text collections. LLMs are not that efficient. They can also do that. They can also annotate a text about whether it is about a topic or not, but they are extremely more resource intense and expensive, okay? You can measure concepts and whether they are relevant or not. You can do frame detection. And we are gonna speak about that a little bit. Obviously, you can compare groups of text. So one section of all newspapers compared. So how does one newspaper cover international issues? How does the other newspaper cover international news altogether? With a mean value maybe, or other ways, we'll see. Finding super typical examples of a topic, of a certain thing we are working on. So you get all the embeddings, compare all the distances with one another, and you get those that have the highest distance, and you get the most typical example. You get those with the highest distance, so not similar at all, and you also get atypical examples, things that are not about the thing we're talking about at all. Yeah, unusual outlier. You can also cluster texts when you don't have labels in an unsupervised manner. We're going to do that as well. And you can, to my eyes, something extremely crucial and very useful as a tool, which is you can compare how embeddings change over time. So assume you have newspaper. So in my example before, that was a cross-sectional data collection effort. So within 1 year, all the articles in the Greek online media. Okay, 2 million articles. But that was 1 year. Imagine if you could do this for a decade, right? And I'm going to show you a paper after this, which is uploaded as well, where they took 100 years of books, basically, and they calculated embeddings per decade. And they compared how the embeddings evolved relative to each other across the years. So when you introduce the temporal dimension here, 385, I mean, no. When you introduce the temporal dimension here, you can do pretty cool things about seeing whether semantically things change over time or they remain stable, right?
we are not lost. We are
No, I'm looking a little bit of nodding here, and I feel like some of you are getting inspired in some ways about time. But if you keep thinking about how this works, you will see that time is an extremely valuable thing here. We will not see it used today beyond the paper that I'm going to talk to you about, but it's an extremely important aspect. And if you get your hands on longitudinal text data, you can do pretty cool stuff with embeddings. And you can improve manual coding, manual annotation with embeddings by, again, filtering or showing the researcher, the annotator, typical or atypical. Again, many researchers have leveraged embeddings to do better manual coding. So you can also compare semantically things between different languages, right? So these models, the one we're going to show today and others that are much more powerful, and we're going to talk about them as well, they have multilingual capacity. The one we're going to see today is not the best at every language, and it's good enough with Turkish. We're going to test it a little bit, but Turkish is included. It has been accounted for, so it can work with Turkish. Imagine a scenario where you have data from multiple countries in multiple languages, and you want to see how budget execution is covered in multiple languages, multiple countries. So you calculate embeddings for each language, and you compare the two, and maybe you see a smaller distance between Turkey and Greece, so they cover budget execution in a similar way. They attack the government more, or they protect the government more, just like this is out of my head. Or in other countries that are a bit more liberal and the media works a bit more freely, they attack the government more, and those embeddings are closer, right? So you can do pretty cool stuff, assuming, of course, that all the language-specific confounders, all the language-specific things that matter and could affect our result are controlled for. Because sometimes the embedding, out of the 384 dimensions, there might be some of those that are due to the language and not due to how it's being covered, something, right? So maybe by default, in Turkish, we speak about budget in a given way, and in Greek, we speak about budget in another way. And that is something we should be controlling for somehow. We can talk about that more if you have questions. All right? Cool. So let me ask you this. So do you see any problem with the way word embeddings they assume that meaning is to be found in text? Do you see any problem with using them like this? I mean, you already identified a couple of things, but yeah.
I have a question, or maybe an answer to this one. So does the number of words on how long two articles is important in terms of calculation? For example, they're talking about the same thing, and they're representing budget deficit the same way, but one of them is more wordy. Some people talk too much, and they use the word deficit more often, but actually they're sounding the same thing. Does it make a difference?
Yeah. So when you calculate embeddings, it's a good practice to have similar length documents, right? Because the length of the document matters for the embedding in the end. So whether two embeddings are going to be similar or different is going to rely also on the length of the text. I don't know how and how it would matter exactly, whether it's going to make them go farther apart or come closer together, but it is going to matter.
But then it makes, in practical use, you cannot have exactly the same length of article.
They don't have to be exactly the same, but they should be close to the same length. So you shouldn't be comparing a sentence with a paragraph, or a sentence with. I mean, you can. We still do it. But it's much more efficient if you compare basically similarity of text is a crucial thing for any text analysis comparative thing you're doing. So I cannot be comparing Twitter data with parliamentary speeches. Well, I mean, you can, but when you compare these two completely different sets of texts, you need to be accounting for other confounding factors, which is length, style of speech, vocabulary being used, right? Sarcasm being there and not in parliament, or maybe yes in some parliaments. So generally, when you compare texts, you need to be aware of these confounding factors and account for them. When you calculate embeddings, length is one of the confounding factors you should factor in and try to work with similar kinds and lengths of text. It doesn't matter if it's a little bit more words or a little bit less. You don't have to be exact. Actually, some people cut down, some social science research cuts down on the length so that they are all the same. But that's maybe a robustness check. You can recalculate the embeddings and distances. So you calculate the embeddings and the distances with the text as is, and you get to a finding. And then in the appendix of your paper, you have a robustness check, which is, let me produce the same embeddings and distances with the exact same length. So I'm artificially cutting the texts at different stages so that everything is the same. If I get the same embeddings and I get the same distances and the same findings, then I have a robust finding here with regards to length. Does that make sense?
Yes, but like, so you can talk about the same topic with like 1 page and 2 pages.
Sure.
If you cut one of the articles in half, only talks about half of the topic, like not the same meaning.
So I don't think you should be cutting. I just think you should be comparing similar things. In my eyes, a 1-page article and a 2-page article is still the same. What is not the same is one sentence versus an article, a tweet versus a speech. That's when I think so. And still, in the case of difference, if you want to compare, fine. But maybe if you want to compare sentence to article, what you have to compare is so the sentence with every sentence individually, and then mean that together, or calculate the embedding here and the embedding for everything as a robustness check. So what I'm saying is, you start with whatever you think is best, but then do robustness checks so that you convince the reader that it's irrespective of length in your case. So length doesn't matter in your case. Does it make sense? Not really?
So
we can talk more later also if you want. Okay. But if you feel like, I'm happy to continue talking. Up to you.
no, I think I understand that there is not a rule for it, but is there a rule of thumb? Like,
yes, the rule of thumb is generally compare defensibly similar texts. So style, length, but not exact, and arena. So as I said, social media and parliament is completely different. It's okay, you can still compare them, but you need to convince me that you are only working with the comparable things and the other confounds are not there, okay? Are not impacting your finding. How you do that, it's up to you. You can do robustness checks, as I said. Yeah, you can compare 1 page to 2 pages because the meaning is there in the 2 pages and in the one. That's perfectly fine. But I need to see some robustness checks that convince me that length didn't matter here. You're comparing speeches from Turkey to speeches from Greece. Parliamentary, both parliaments, perfect. But I need to know if language is not a confounding factor here. Okay?
Can I ask a follow-up question?
Of course.
For the robustness check, you're done cut the text so that they are of the same length, right? Is that do we cut the text from?
So normally you would.
Do we is there randomization?
So normally you should do bootstrapping is called. So you cut at different parts. So you do a multiple robustness check. So you check again and again with different cuts. Yeah.
I think also I'm thinking from the realm of poetry as a literary scholar, poetry and translation, because usually, especially in poetry, one word, like words are chosen so carefully where it's intended as a pun or there are layers of meaning to it. So the machine is basically giving you one interpretation and setting it out as the meaning. I was wondering if that is something. And translation too, there's many ways a sentence can be translated, and that's why we say translations aren't sort of direct transfers, but interpretations. And
Of the person doing or the machine doing. Yeah. Pretty important comment. I mean, obviously you are here because you would like to hear about how these tools could be used, but you're all here with a critical mind, and you should be with a critical mind. I mean, nothing that we say here is the perfect tool to do something incredibly well, but it can definitely not be assumed that it will carry all the meaning that an author of a poem wanted to bring in. Sometimes, and this is what I want to talk about now, the reader also brings in their own bias. So if I read a poem and you read a poem, we're going to have potentially we were going to see semantically different things, maybe completely different than what the author intended. So let's talk about this a little bit. Generally, words can be in the same sentence for many contingent reasons. Language is one of them. Arena is one of them. Length is one of them. You don't have enough length because you're writing a newspaper title, so you have to pick carefully how you're going to use the words so that you draw attention, or you make the article clickable, or it carries the meaning that you want it to carry. But then when you start reading the body of the text, it's completely different than the title, right? You know, it happens a lot. So if you're comparing the title with the body, so if you have a corpus of text only titles and a corpus of text only bodies, I'm going to challenge this decision that you made. Because why words are together is extremely important. And why words are there can matter with different biases. Let's see some. So we, as humans, we interpret the world in some reasonable enough way that makes sense for us, but also ignore other and a lot of stuff, right? That's called the reader bias. So when I'm reading a speech, an article, a poem, as a reader, I have my own biases in my mind, so I understand things completely differently than another person. So this matters a lot about how I address meaning, and I figure out what the meaning is of something. The model has its own biases as a reader of a text when it assigns that vector. It assigns a vector with a reader bias, and the reader bias of the model is what data it has seen in its training. So we need to think about that. At the same time, the reason why certain words are there has to do with other processes than that of meaning. There's the speaker bias. I mean, I'm writing a poem in a certain way because that's how I like to speak. But maybe if another person speaks about the exact same thing, they're going to use another language because that's how they learned to speak, right? I grew up in a house with a certain vocabulary. Someone else grew up in a house where other vocabulary was used about the same thing. And I'm a parliamentary speaker that represents less educated people, or more agricultural, rural people. Maybe in my party we choose to use a language that refers to them more than the civil society people or the urban people, right? So I make a decision to speak about a topic in a way that echoes in their ears much better than in other people's ears, right? That's the speaker bias. So by assigning a vector, we are sort of blurring all this a little bit. We are sort of putting it under the rug. And we assume that in one of these 384 dimensions, some of these biases might be included, hopefully are included, but there's no guarantee that this happens. That's why you need to human validate what the embeddings are telling you. Does this make sense?
Is it possible to make the embedding biased? That is to read, for example, a point in a political, for example, mindset. So I want the embedding itself to be biased in its embedding. Is it possible to fine-tune such a matter?
So you want it to be biased?
Yeah, I wanted to read it in a specific interpretation.
Yeah.
So can I fine-tune the embedding model?
Yes. Well, you can fine-tune as well. You can fine-tune by, apologize for the thing, it's for the throat. So fine-tuning is a little bit of a different scenario, which is more about giving a character to an LLM or having a model, making a model a bit more capable of classification, about the classification task that you want. When it comes to embedding, I'm not entirely sure if fine-tuning is going to make a difference, but you can potentially play with how you define the topic initially. Let's say you are trying to figure out how many articles are about a given topic, right? Let's say this is your task. Here in the beginning of the task, you need to define what the topic is and get an embedding for that definition. And then take that embedding and go to the text and find all those embeddings that are similar to this definition of yours. So you can play with that definition. You can make that definition longer and more precise. You can make it biased. You can make it sound one way rather than another way. So you can play with that definition as much as you want. And that's where you would introduce bias in my eyes. Yeah. We're going to do that, and you can test also. Okay. So there's this Kozlowski et al. paper that I added in the drive. I urge you to take a look at it. It's really innovative when it happened. It's still innovative. I think it's extremely cited. It's really nice embeddings for the social sciences paper. It's one of the really cool papers about what you could do with embeddings conceptually, semantically, in large corpora of text, okay? I'll go a little bit over it as if we were in a class in university, and I'm sorry for that. This is a workshop, I know, but I think it's really cool to see what you could be doing here, okay? And we have plenty of time to work on code, and I'm sure you've seen a lot of code already in these days, so that's fine. So they use embeddings so that they can gauge, measure, shared understanding of what social classes, okay? They get text from millions of books published over 100 years, as I told you, okay? All the text, everything in one collection, okay? And what they found, they validated with surveys as well of people in different countries, of authors of books, readers, and different people as well. But mostly in different languages as well. So they produced word embeddings based on this data and the model they had. And what they did is they made pairs of antonym words for each dimension that they wanted to work on. These are dimensions that have to do with social class, and they are informed by theory, okay? We care about what sort of dimensions we can think matter for class. Being rich or poor is a clear dimension of class, right? So one antonym pair is rich and poor. Another one is feminine, masculine. That's also matter. Rural versus urban is another one as well. And then what they do is they project important words on this dimension that they have, which is on the one side poor and on the other side rich, on the one side feminine, on the other side masculine. They do that for sports and for other things and activities, and they want to see if certain activities are more for the poor, more for the rich, certain sports, certain foods, certain concepts. Anything is more on this side of the dimension or on that side of the dimension, based on these 100 years of book data, right? How would someone write about playing golf in a book 100 years ago versus now? Is golf more associated in this text corpus with being rich or with being poor? What would you guess? Would your guess be?
Rich.
It's a clearly upper class sport. Tennis is one of those. Football, on the other hand, is on the other side of the dimension. Food is really cool here as well. You got caviar, for example, clearly on the rich side. You have hot dogs clearly on the other side. I mean, I love them anyway. And what they can do, because embeddings can be multidimensional, is they can intersect multiple dimensions. So imagine you have the rich-poor dimension and the feminine-masculine dimension, right? You can find things, concepts, foods, activities that are more for rich men or for rich women, more for poor men or poor women. And you can add further dimensions to this because we're talking about embeddings. And you can do, again, pretty cool stuff. So let's see what they do. So they get these antonym pairs: poorer, richer, poor, rich, poverty, affluence, so on and so forth. And they establish this one dimension, this one axis here, that is the affluence axis. Either you're poor or you're rich, something like that. One side very rich, the other side very poor. And then they project names of sports. Let's talk about the sports aspect, they do more, onto this affluence dimension. So on this axis and this, is it elliptical line? I mean, half a sphere, you know. Anyway, on this, let's call it elliptical, even if it's wrong, you let me know. So on this line, let's come again. Semicircle, maybe. Yeah, circle. Semicircle is better. The sports they have and the embeddings for those sports are placed on this dimension as a result of how similar they are with the rich and the poor embeddings that they calculated, okay? We are going to be comparing embeddings vectors with something called cosine similarity. And that's a geometry term. I don't know if you heard about cosine, sine and cosine. It's a way of measuring angles, right? I see some nodding, but not everybody is nodding. What you should care about. So, good, if you know the word in Turkish, maybe I can say it, yeah. Yeah. Is everybody familiar with cosine, sine? I mean, you don't have to remember everything, but let me take you here to this nice example. So the way we compare vectors, embeddings, is by looking at their angles, right? We're not directly measuring distances like that. I mean, we can also do that, but mostly we care about angles because, okay, in a two-dimensional space, I can measure this distance. It's easy. It's a line. But when I add the third dimension, the distance anymore is not about a line. It's about a plane. I don't know if this makes sense in your minds, but the distance is not a line anymore. It's actually a flat area. So in order to calculate this flat area, I need the angle from here to here so that I capture this. So we use cosine similarity. So the way we compare embeddings is by calculating cosine similarity. So again, I don't want to spend time on this, on the mathematical aspect of this. You're welcome to do. I don't even understand it 100%. I just use a function in Python that calculates cosine similarity, and I'm done with it, okay? But you should think about comparing embeddings and vectors as in comparing angles, okay? The angle is the key here. So to go back to what I was saying, the way the sports are placed here have to do with their angle distance, angle similarity to the rich and poor embeddings, right? And tennis and golf, their embeddings have a smaller angle, have a smaller distance with the rich embedding. So they fall more on this side of the semicircle. Camping, boxing, at least in these 100 years of books, fall more on the poor side, okay? And then you have some in between, like basketball and soccer, baseball. Mm-hmm.
Is it something like the context they give about the golf, like golfing in a rich area and boxing in like Harlem?
Yeah. Has to do with when the model read all the text, when the word golf appeared, what other words were around them, and what meaning those words carry with respect to the poor-rich thing as well. So it could be location, so whether it's Harlem or Upper Manhattan, if it's other words for affluence, rich, like clubs versus organizations, or could be many things. But yeah, they check the kinds of words that come around golf and appear together with golf in this 100 years of books, and they calculate an embedding that ends up being much closer to the rich embedding than the poor. But that's based on the text it has, right? Maybe nowadays more people can play golf. I doubt that, but maybe now it has moved a little bit more. So if we introduce the time component, we could see whether baseball was here in the 1900s and whether it's here in the 2000s, so 100 years later. So you see if it moved in this axis, you can calculate if it moves left or right, and you can do pretty cool stuff with it. Yeah. And then here we have only one dimension, this affluence dimension. But let's say we add another one. So they add one more, which is in this case the feminine masculine one. And now instead of a semicircle, we have two semicircles which create this hemisphere.
Sounds good.
Maybe. So there's a hemisphere now. I don't know if you can visualize it and see it. I think they're doing a great job, but it's here. So now sports are... Yeah. Come again?
Intersectionality, actually, what we call in social science, intersection of class and gender.
Exactly. So we have different parts of this hemisphere that are more feminine and rich, feminine and poor, up here masculine and poor, up here masculine and rich, right? So where its sport falls in this, how can I show it? But imagine there was a ball here that's a hemisphere. Wherever it falls here, its embedding falls here, matters for whether it's more rich or whether it's more feminine or masculine, right? So we can do this because we have the embeddings. It's the embeddings that allow us to do this placement, this geometric placement. And this is only with 2 dimensions. if we were to add the third one here, we cannot see it. We went from one axis to a semicircle, and the moment we added a second dimension, we went to a sphere, which is already 3-dimensional. So if I add another dimension, we go to 4D, and we cannot think of that already. So for visualization purposes, for a paper, that's all we can do. That's up to here we can go. We can add more, but mathematically you can go more. And you can compare much more. They do that. In any case, the cool aspect is the time component, as I said. So what they do is they get the mean embedding for each one of these class components. So you have gender, you have affluence. Well, affluence is the one they compare with cosi similarity. So these are aspects of class, right? Education, cultivation, status, morality, employment, and gender. They are all aspects of social class, together with affluence, being rich or poor. So they take and they calculate for every decade a mean embedding for each of these things. So they take all the text per decade, they take it in one, and they calculate an embedding for that decade for morality. They calculate an embedding for education for that decade, so on and so forth. Then they go to the next decade. They take all the text there, and they calculate a mean embedding for all of these dimensions. And then they plot these across dimensions based on how similar they are to the affluence dimension. So they want to see if education is more similar across the years to being rich or poor. If cultivation is more, if gender is more similar to affluence, being rich or poor across the years semantically. And what they saw is that, with the exception of education, which as time goes by becomes more similar to being rich or poor. So back in the 1900s, being educated was not as important for whether you were rich or poor as it is in the 1990s, right? According to the books that we have at hand. Semantically, being well educated is much more related to being rich in the 1990s than it was in the 1900s. According to these 100 books, right? Imagine you take parliamentary speeches for 100 years in a parliament. You have data sets like that. And you see how parliamentarians were speaking, or parties were speaking about certain topics per decade. You can see the involvement, the evolution of how they speak about something over decades, right? And you could do something similar like this. Pretty cool, no?
Morality is decreasing.
It's not like it's decreasing. It's similarity with being rich or poor is decreasing. So here in the 1900s, I mean, it's not a big difference. 0.2 to 0.09 or something like that at the end, right? So it's not a big dip. Basically what they're saying is that generally these concepts sort of remain stable with the exception of education, which increased a lot. Morality is going down indeed, but it's not going so much. I urge you to read the paper. The finding here is that, okay, indeed morality is going down, but it's not that big of a difference. But in any case, what this line is telling us, the yellow, is that the distance semantically between being moral and rich was bigger in the 1900s than now. So it was more moral in the books, more moral in the books to be rich in the 1900s than it is now. It's become less moral to be rich, something like that. Yeah, rich people are less moral in the 1990 now than 100 years ago. But the distance is small, so they don't overstate this. They say actually it's sort of stable.
I'm sorry for interrupting.
No problem.
Trying to simplify the visual. Is this something like positive correlation and negative correlation? Like it goes up, there's a positive correlation between education and affluence?
Yeah, sorry, I should have said that. So cosine similarity goes from we care about 0 to 1. So the more closer it goes to 1, the more similar two embeddings are. Okay, closer to 0, less similar. If it's negative, it means they are going completely opposite direction, so they are sort of uncomparable or completely different. Okay? I'm checking my colleagues to see if I said that right.
So it goes closest to one means like they are
1 is absolute similarity.
absolute similarity.
Exactly the same embedding, the same vector, which is not possible.
So education almost goes parallel with being rich and poor. This goes because it comes close to rich.
No, education had a distance of 0 cosine similarity of 0.15 in the 1900s. So in the scale of 0 to 1, it was 0.15 similar. So when I ask you the Obama and president, your colleague said 0.7 similar, because I gave you a scale of 0 to 1. So think about it the same here. So in the scale of 0 to 1, in the 1900s, education and being rich or poor, being rich, was 0.15 correlating. Their embeddings were 0.515 correlated. In the 1990s, the embeddings of education and affluence, being rich and educated, grew to 0.4. So they are much more similar. The embeddings are much more similar. Does that make sense?
It does.
Anybody else needs a more clarification here? Like we could read this again?
You mentioned that they were taking the mean values of the books, right? The mean.
For the decade.
Okay, for the
Per decade, yeah.
This mean value represents the average, what the average book says about the subject, right?
Yes.
With the morality, the fact that the morality is decreased, it means that the rich people becomes less moral, or the poor people become like a bit more moral.
That's your interpretation. No. It simply says that in this collection of books that we have, the word moral, or whatever words we decided are about morality, the morality dimension, however we constructed it, the embedding for that morality is closer to the embedding of whatever we use to construct the affluence, the rich-poor dimension. So it really depends on your choices as a researcher on how you constructed that morality dimension and that affluence dimension that tells us what this means. Okay? It's not about moral people, rich people being more moral. It's richer people being rich, being closer semantically to being moral in this collection of books. So closer semantically is not is or isn't, right? It's closer semantically, whatever that means within the context of doing text analysis. So interpretation is extremely key here. Like we're still needed as researchers, so it's not completely automatic. Does that make sense?
Yeah.
Is it being rich or like the dependent variable of affluence? Like affluence
Yeah.
is mentioned together with education or being.
No, they are separate apparently. Again, it's been a long time since I read this paper, but and you can read it, but they define a dimension as antonym pairs. So the more antonym pairs you put in there, the more words you put in there, the more well defined the dimension is, but more computationally heavy to get, because you have to get embeddings for every one of these and then compare with every one of the other dimension, etc. So, and they wrote this paper many years ago. So computationally, if you were to redo this paper, you would do a better job. Actually, it's a good replication idea. Yeah. Any other question? Okay, let's take a quick break this time. Not more than 10 minutes. Please be back in 10 minutes. And then we wrap this up and go for lunch. Wrap this first block, okay? Cool. So everybody has access to this Colab notebook. Is there anyone who doesn't have access to their notebook? I mean, once again, as we did with every other course, you're welcome to just look at the screen and while we do, but you're urged to do these things actually on your machine. I mean, that's the purpose. That's why it's called a workshop. And let me ask you something. Like, you have groups already, right? So first of all, I'm sorry that I came a little late, and I'm not sure how the projects are going, but we have a lot of things to cover today about embeddings, and I think everything is useful, but we have a couple of exercises here that are relatively simple, but they still take time, and it requires you working on it. And I know there is time for you to work on your projects after dinner, right? That's the schedule. But because it's Thursday, and I think that happened the other time as well when it was Friday, like if you think you need a little bit more time to work on your projects, potentially maybe the very last section of today's class, we can dedicate on you maybe implementing this stuff on your projects instead of just trying to do this exercise, which you can do later on because you have access to these Colab notebooks anyway. How does that sound?
Interesting.
Okay, cool. So let's see how we go after lunch, and we can maybe stop at a certain point, and then you work on your own stuff. But obviously, you're also welcome to do this. So what we will do in this workshop, I mean, we talked about what an embedding is. We will try to see how and why similar texts end up close together with embeddings. We will calculate embeddings for texts. We will see how to use them for semantic search. We'll also do some 2D and maybe 3D visualization as well. And we'll try to also see clustering and some other techniques. I mean, again, a lot of things here. But before we start, let's do some setup. So similarly to before, if you click on this line here, you will get this LLM workshop file here on the file structure with some data in it. Everybody has that now? Anybody who doesn't? You don't?
I got an error.
So what kind of error?
I'm not sure. It just gave an error. Like not like code error.
It doesn't say.
Something different. Okay, it worked.
It worked. For you?
I'm checking.
Okay. I mean, no pressure, eh? I mean,
Should we set for CPU or it doesn't matter?
come again?
So should we set for CPU or it doesn't matter which one we prefer?
So everything we do today can be done on the simple CPU instance. So we don't need more, no high RAM, no nothing of that. But who here has a Colab Pro account? So without the Colab Pro account, what kind of GPU access do you get? What options are available here? G4 GPU. That's kind of nice. I didn't know that.
Maybe for just a short amount of time.
So maybe there is some, yeah, that makes sense. Yeah. Okay, cool. So anyway, if you get a Colab Pro account, which is not, I'm not recommending this, but some of the text analysis things that you've seen in the previous lectures and today are going to be obviously much more efficient in a server with more GPU capacity or in a local computer with a graphics card. I mean, I'm looking at your laptops. I don't think anyone has a distinct graphics card. I think you do. Yeah. Okay. So, and you do? So, and you do? No. So, with the exception of two colleagues of yours, nobody has a distinct graphics card in your laptop. So, you cannot really use GPU acceleration, but something you need to be aware of, right? So the more data you're working with, the more complicated things you do, GPU acceleration is extremely crucial in our analysis. But wherever we're going to do today, and more actually, can be done in a CPU-only system like your Macs. So don't worry too much about it right now. I mean, you'll get to that problem when you get to that problem, and it's taking extremely long to run something. Yeah. So when you click that thing, it goes to a GitHub repository and it brings some files in. The important thing is this AG newspaper data.csv file that is here and contains some articles, some open source media data that we can use. Please install also the sentence transformers library, because that's the library we use from Hugging Face that allows us to use embedding models to calculate embeddings, okay? Quick reminder about Hugging Face. So you remember what Hugging Face is, right? It's our favorite repository of open models, open weight models. Here on the top, if you type embeddings, you have to remember the right way to type it. So you have 1,473 models that do embedding calculation, right? They are made for doing only that, calculating embeddings. And I mean, as with everything on Hugging Face, you can see how many times it's been downloaded, when it was lastly updated, how big it is, and what it's meant to be doing. These are all feature extraction models, so they extracture these dimensions, these features, right? So you're welcome to use other models if you want. This model from Google, the embedding Gemma, 300 million parameter, I mean, is one of the I don't know if I can say state of the art, but it's used a lot in my field of political science as well. But it's computationally super heavy. Like we wouldn't be able to use it now for what we are doing. Like it's very heavy. You need more computational power. But I've recently published a paper using the model we are going to use today. And when I say recently, in the past year. So there are less important models. As long as you validate and you check the outcome, you can still do stuff with less state-of-the-art models as long as you validate, okay? So let's see the data set as well. So this line here is meant to make the text appear a little larger in the box, so you're welcome to run it or not, it doesn't really matter. But wait, I think it needs, so this import pandas as PD, you should put it here, sorry. Otherwise you probably get an error if you don't run it first. And then let's import the newspaper data with PD that reads CSV. I mean, simple stuff. You're pros now in Python coding, right? And getting CSV data into a pandas data frame. We don't have to talk about all of that. And let's check this data frame a little bit. Is everybody at this step loaded the newspaper data? Is anyone that's not on this step? Cool. So this is a 3,000 rows data set. So there are 3,000 articles here, right? But this data set is just a sample version of the full data set of the AG News. The AG newspaper data is actually 120,000 articles, something like that. We're just getting a 3,000 sample just to work here today, okay? Below a bit further down on the notebook, with this block here, you are welcome to download the full thing if you want to run the full thing. I mean, most of the code is going to take longer to run, but it can still be doable. It's still doable in the CPU only one, okay? You're welcome to do that for your project, for example. But I don't know if which of the groups here, can like one representative of each group, by show of hands, tell me if you're using your own data for your project, the summer school project. Like raise your hand if you're using your own data.
The data that we...
So for the project, are you using some existing data or your own data?
Our own, our own data.
Collecting.
New data.
You're collecting it, so your data. Collecting. So everybody is using some data collection thing right now. Excellent. Okay. But obviously, if you're not collecting, you're welcome to use some existing data set like this. Or I mean, again, you're not bound. So Right. So this is the example dataset we're going to be using in this workshop today, and it has 3 columns. So there is the title of the article. This is just the title. Then the description. I mean, the names of the columns are not great, but so this is the body of the article, actually. And then you have the class. So the category, the topic of the article. This dataset is out there for training algorithms, for training models to classify category, and that's why it comes like this. But it's a useful thing for the semantic stuff we want to do as well. It's very useful normally to combine the title and the body into one column, okay? So that we are not working with 2 separate things together. So we are working with one column, article, we can call it article column. Majority of text analysis algorithms normally use the word text. So it's good practice to use that as well. But I mean, it's again not obligatory. So with this line here, we are creating a new column called text. And inside we are combining the title plus the description, so the body. We're putting that together into one new column, okay? If you run this, you should see a new column here called text that contains the entire thing together, okay? So about the classes, in this 3000, it's a balanced data set, so it's about 700 of each classes, science and tech, business, sports, and world. Forget about this, you can check it later as well if you want. So this is the data set we're working with, and for our purposes, we spoke about what an embedding is. Again, just a quick reminder, texts with similar meaning should have similar numbers, similar vectors, similar embeddings, similar representations. Okay? I think that should be clear by now. That's the key thing we need to do. So an article about football should be close to another article about basketball, or at least should be closer to an article about basketball than an article about politics, right? Something about the stock markets should be closer to another article about companies, etc. And in order to do the embedding calculation, we're going to be using the all mini-LM v2, which if I go to Hugging Face, it's from Sentence Transformers. We see that last month it has been downloaded 250 million times. So it's an insanely used model. It's people use it a lot. It's very useful, very efficient, and very good performance. Okay.
Reliable.
Yeah. It's also multilingual. So yeah, you're welcome to read the model card if you want. And everything we do is based on 2 libraries: the transformers and the sentence. Basically, only the sentence transformers libraries, to be honest, I think we'll be using today.
Do you have to download this separately?
So I'll show you in a moment. Yeah, you download it once, it gets cached, and then works. If you're using your machine, it would be downloaded once and that's it. But because we are in Colab, if you download it and then you close the notebook and open it again, it reconnects to the server again, you would need to download it again. Yeah, that's the problem, the unfortunate thing with Colab, but I mean, it's useful in other ways. But yeah, the idea is that you download the model only once in the beginning in your machines, and then it will work automatically.
So it also increases the download numbers on the Hugging Face. If people prefer to use it on the Colab notebooks.
That's a great point. Potentially these are inflated, but also when I open a Colab notebook and I click on the model to be downloaded, I think they have a way of distinguishing where the request is coming from and if it's a Colab with the same account. But I guess they have no reason to not say everybody's downloading this. But I mean, if I check another embedding model is not going to have this amount, right? So it's really not only about Colab being used to download it, but great catch, yeah. So let's download the important packages that we need, import. And here this block is the one that downloads the model. So if we all click on this, let's give the model how many we are, like 30 more downloads for this month. In my case, because I connected this morning, it only took 4 seconds because it was cached already. It was in the memory. I don't know in your case how long it took. Come again? Okay, not bad. Okay, my favorite example of Obama speaking to the press. Okay, so we have 2 sentences here. Obama speaks to the media in Illinois, the president speaks to the press in New York. You can run this. Now the way we calculate embedding is as simple as this. We use the word model, which is the object that we created before with sentence transformer, and we put inside this model, and we type .encode. So the .encode function is calculating the embedding for this sentence. So in here, we should put the text that we want the model to encode, okay? I could simply put this sentence in here, and it would calculate an embedding for this sentence only. But I am passing a list. A list is square brackets separated by comma, and I'm putting 2 sentences. You can pass a list with 100 sentences, 1,000,000 sentences. You can pass an object from a data frame with 1,000,000 rows, okay? So whatever you pass here is going to calculate embeddings for all the things that are in there, okay? In this case, it's going to calculate 2 embeddings, one for sentence 1 and one for sentence 2. Right? So run this. Again, should be extremely fast. And we can check the first embedding in this, because now it has 2. And look now. It's an array with a lot of numbers. A lot of dimensions. Can someone tell me how many there are here?
384.
Bravo. So this model gives back 384 dimensions. Other models do other, the way we discussed before. So if I do len, I guess. Again, my programming is getting worse with LLMs. Yeah, 384, okay? So this is what an embedding looks like in real life. So it's a combination of numbers, 384 numbers in this case, that represents sentence 1. Obama speaks to the media in Illinois. The model assigns these values because it thinks each of these values carries some meaning about this sentence. The way Obama is used, the meaning that the word speaks carries, the full stop used, punctuation, whatever, a word order, all of the things it thinks matter. And they are not defined. It's just a model that is doing this job. We don't know exactly what it chooses and why it chooses each thing, okay? But this is an embedding. It's not easy for us to read as a thing, right?
Yeah, this one's I was going to ask, like, how it decides what kind of meaning is assigned to what? What is embedded to what?
We don't know.
Does it depend on how we train the model, for instance?
I think this is a reasonable assumption to make, but I don't think we know how its dimension is, what its dimension means here, what this 8.7 means versus this 2.8 here. What we know is that for the model, the combination of these values carries the meaning of this sentence.
If you don't mind,
Yeah, of course, please.
The idea is like this. Think of these numbers as word frequencies, but not just 300. Think of all the words in the English language, so probably tens of thousands or hundreds of thousands. Okay, so my vector is hundreds of thousands dimensions, and each cell tells me how frequent is or how many times that word appears in the document. So I have a huge vector, hundreds of thousands of dimensions. And then there are, but I can't work with such a large vector because I have a very large vector, but I have one vector for each document. So I have many documents, many vectors, many words potentially, So I have a lot of information, a lot of redundancies, a lot of zeros, because I have 100,000 words, but not all these words will be present in my data set. So there's some fancy mathematics that they do to compress this huge table, so that instead of having 100,000 dimensions, I will have just 384. Once I compress, these will not be anymore the frequencies. These will be some non-interpretable stuff. They won't mean anything, but they will preserve the geometry. So again, if you start from a word frequency assumption, so where each cell is the frequency of a term in your text, you get enormous, ginormous web vectors. Then you do fancy mathematics, these models do fancy mathematics to compress these vectors. So moving from 100,000 dimensions to just 300. When I compress as a result of these mathematical operations, these are not anymore word frequencies, they are just latent dimension. They call it latent, which means, well, latent.
Not obvious immediately.
Not obvious. So hidden or some kind of obscure dimension.
Yeah.
What is cool and what Yani is showing you is that we cannot interpret each number, but in the n-dimensional, multidimensional space, these preserve the properties of being closer if their meanings are closer, if the words they contain are closer in meaning, and so on and so forth. I hope that makes sense and does not confuse you even more.
That was an amazing explanation, Maes. Yeah, that was great. But I think we are trying too hard to figure out what each number means, and I think the important thing is that.
No, I was like, we said the model assign a meaning. How does it?
Yeah, so I use the example of having a vector for me, and I said one is my age, the other thing is whatever, and I think that's not representative of what actually happens in these values here. So what I now understand as well is that, I mean, these are just numbers that in some way continue carrying the meaning that the original huge table carried, but with much reduced information, and we can still compare these, we can still use these to compare two sentences or two documents or whatever, and still carry that meaning that allows us to do the semantic comparison. So it's not exactly tied down, put in paper dimensions that the model is using, and we are asking the model to use that are coming there. So we shouldn't be thinking about it like that. This was just an example that I think primed you to think about these dimensions, but it doesn't work like that.
So it's similar to principal conform.
We are going to use that actually, yeah. I don't think it's similar. It's much fancier, mathematically speaking, to principal component analysis, but it is dimensionality reduction.
It's the same similar approach. It's called the singular value decomposition. But it's a way of taking a matrix and subdividing it into multiple matrices, and one of these matrices that you get is exactly that.
Yeah.
So it's the same principle of having crazy high dimensions and reducing them, compressing them. But then the things you get at the end have kind of no relation in meaning to what the numbers you see there.
So there's no value for us in trying to interpret what a vector contains inside in singularity on its own. Like that doesn't tell us much, okay? What tells us something is calculating cosine similarity between two vectors, okay? As I said, close to 1 means very similar, around 0 means not very similar, negative values means they point in different directions. Again, because we were thinking about angles, right? So from sklearn metrics, scikit-learn metrics, we have cosine similarity. That's what we imported before. And it's a function that calculates this angle, the cosine of the angle of the two vectors. So embedding 0 and embeddings 1. So inside here, I'm passing a list again of the two vectors, so of the two vectors that I have. And if you run this with .item at the end, you get the full value. So these two sentences have a similarity of 0.61. If you round the value as well, you get this as well.
For the article, what they did is rather than putting like embedding 0, they put like cultivation, an average of cultivation embedding.
For the paper?
For the paper, like the cultivation, they have the cultivation, like data and things like that.
So in this script, we are working with document level embeddings. So embeddings for a sentence or a collection of words. In that paper, it was a bit earlier years of embeddings for social scientists. They did it on the word level. So it's a little bit different than this. Beyond that difference, they got key antonym pairs for each dimension. So for the affluence dimension, for the affluence dimension, it was these antonym pairs. So poorer, richer, poor, rich, poverty, affluence, inexpensive, expensive, impoverished, wealthy, among others. These are the ones they show, but they have a complete list. Okay, and they do this for every one. So they calculate an embedding for this, then I calculate an embedding for this, then for that, and then they mean the embeddings. But that's the word level. We are now working at the sentence level, the document level, okay? So the embedding we are getting, this thing here, is about an entire document. In this case, it's a sentence, but here, imagine it could be an article, the entire article, as we're gonna do later. It could be a speech, it could be a tweet, it could be whatever, okay? A YouTube comment. So, according to, so if we calculate the distance between the two vectors, they are at 0.61. I think you said 0.7 earlier on, when we said how similar you think, so you are extremely close. Great job. So according to cosine similarity of these two embedding vectors, these sentences are close to 1, so it means they are very similar. Very close to 1. Over 0.5, it means they are very similar, okay? So they share no words, but semantically, with embeddings, we get a score that tells us that they are similar. 0.6 is a high score generally. You will see it's not easy to get 0.6 generally, it's a high score. You are welcome to use any other model. So instead of doing model sentence transformers and add this, you are welcome to do sentence transformer and add another model here from Hugging Face. You're welcome to try whatever you want. This is another one that is sort of common, but it's way slower than the one we're using. So if you try to load this now and do the same thing, it will. So I'm gonna load it. I hope it's still cached. No. So yeah, it's cached. So otherwise, it takes around a minute to load. And if I calculate again the embeddings with this model, and I do cosine similarity again, it takes a little bit longer to calculate these embeddings. I get a score of 0.74 here, so a higher score. So the embeddings that this model produced are different than the embeddings that the other model, the first model produced. And according to the second model, it happens that these sentences are even closer in meaning, semantically. Does that make sense? So again, you're welcome to use any model. So I'm going to go back to the other one because it's a little bit faster. So I'm going to just run this again. I mean, you could create two objects, right? Model 1, model 2, and also compare. You can do many things, obviously.
Can we say that this other one, which is slow, is more accurate in predicting?
If you think that 0.74 is more accurate, yeah, but I guess you said 0.7, so you think it's more accurate, but no, I'm joking. But I think it's more accurate.
Okay.
I would say that these sentences are close to 0.8, maybe similarity, but that's my brain. 0.7 is extremely close to that value. 0.6 is also close. So I'm not sure if it's more accurate, but potentially because it's a bigger model, it's going to have a better performance, so it could be more accurate. Yeah, that's a trade-off of performance and resource. How many resources it uses. So, as I said, instead of just putting a list of 2 sentences in the model, I can also put a list of multiple sentences, right? Let's see what happens if I put 4 sentences in there. So we have that is a happy person, that is a happy dog, that is a very happy person, today is a sunny day. We have these 4 sentences as a list, right? Bracket separated by comma, 4 different sentences. And we calculate again the embeddings, and then we also create an object called similarities where we put all the cosine similarity between the embeddings against all the embeddings. So one by one is going to create cosine similarities comparing one by one every sentence, right? So the embedding of this sentence with itself, with this one, and this one. Make sense? On a one by one aspect. So if you run this line, you will get an array like this, and you have 4 times 4 values cosine similarities, right? And if you've seen a table like this, a one-on-one comparison, normally this diagonal line, these values here, are all the same because it's the same sentence with itself compared to itself, right? So this very first value is that is a happy person compared with that is a happy person, and it's extremely close to 1 because it should be, right? It's the embedding, it's the same word. Yes, exactly. Also, this value is the same as this value, because on one hand, this is compared with this, but then when we come to this sentence, this is again compared with this one. So they are compared twice. I guess there should be a faster way to do this, more efficient, but I mean, it's also not taking too much time. So normally what we do is we remove this diagonal, we replace it with -1. When we try to find the most similar sentences, we replace these values with -1 so they are disregarded. Okay? So all the diagonal, we don't care about it, we replace it with -1 so it doesn't show up when we try to find the most similar sentences or something like that. And we do this here. Fill diagonal, -1. And then we create something called the max similarity index, which gets the highest similarity it can find in this table, right? And then it gets an index for that, so it tells us it's this or whatever. By the way, this is the highest similarity it finds. And then we simply print the 2 sentences here with a script that it thinks are the most similar. So the 2 most similar sentences are, this is a happy person and this is a very happy person. And would you agree that these are the most similar sentences in here? In these 4 sentences? Yeah. And clearly in my eyes, this is also the least similar of all. Like if we were to see what's the odd one out and we wanted to exclude something, we could also check the average similarity of a sentence to the others. So we could average per row. So these are all the similarities of the first sentence towards all the others. This is all the similarities of the second sentence towards all the others, so on and so forth. So if we do row means, we will get the average similarity of a sentence to the entire corpus. And we can get the ones that are really low in similarity, so they are very different than the others and maybe exclude them. Or we can get the ones that are super similar and only keep those. There are multiple ways of going about this. Does this make sense? Okay. So let's quickly do this and then go for lunch, okay? Let's play with a king minus woman plus king minus man plus woman is equals queen example, okay? It's a toy demonstration again, don't put too much meaning in it. So here we create a list of words. King, queen, man, woman, the ones we care about, prince, princess, president, football, bank. Is there any word you would like to add here that would make things more complicated for the model? Anything that's closer to queen that we don't wanna use, that we wanna use it to confuse the model?
Knights, maybe.
Come again?
Knights.
Knight?
Royalty.
Any queen's name?
Empress?
Elizabeth.
Regina. Well, it's like a Latin for queen, no? Actually a good idea. And maybe we use also, I want to use a name of a queen. Victoria, I like Victoria. Yeah. Okay. Like queen and Victoria are practically the same word, so I want to see what's gonna come up there. Okay.
Can I also check for Turkish?
You can do it in the exercise right away. So after this, you have a chance to do this on your own. Okay. So what we do is we put all these words and we ask the model to assign embeddings to each word. Okay. With model encode, the model we have in memory is using the encode function, and it's going to calculate one embedding, 384 dimensions for each word. Okay? Then we get the IDs from the list of words for king, man, woman. And now we do this calculation. Now we do this thing. This is what we are doing here. King minus man plus woman equals hopefully queen. So we create an object called analogy vector, and we created this word embeddings here, right? This object holds, this object holds, it's an array with 14 word embeddings, because the list of words we fed it was 14. So it contains one embedding for each word, okay? 14 embeddings. And if I do word embeddings 0, so to see the first one, again, like before, it's just a word embedding. It's an embedding of 384 values, right? So here we get the word embedding for king minus the word embedding for man plus the word embedding for woman. And this will be a new embedding that is produced by this mathematical thing that we're doing here, one subtraction and one addition. Does this make sense? So if you create this, takes 0 seconds to create, then we create an analogy vector with all embeddings, so everything in there. So we are comparing this vector with every embedding in the document in the other words. So now we have a new word, a new embedding that is the outcome of this mathematical thing, right? We have a new embedding for this mathematical thing we did here. So now we take this new embedding and we compare it with all the embeddings of each word here with cosine similarity. And we expect that the highest cosine similarity is going to be the one with the word queen. Hopefully not Victoria, hopefully not Regina, obviously not football, and not bank. Does that make sense? So let's see what happens. So we do the analogy scores, and we create a data frame that if we check, looks like this. Wait. We can remove the words that were used in the calculation, so we can remove king, man, and woman from there because we don't want them. And then we can run this. So this was before we added those words, and queen was indeed the top similarity score. So the outcome analogy vector, the outcome vector of this mathematical process was closest to the word queen than any other word in that word list that we had. So indeed, this mathematical thing turned the word queen back. Okay? It's closest to the word queen than any other word. But let's see with the new words that we have. Queen is still the most common word, more than loyalty, princess, empress, president. Actually, Victoria is quite low. I'm surprised by this. Regina is even lower. Come again?
If you write Elizabeth, it would be more similar.
Than queen?
Yeah.
Wow. Let's try. With Z?
Yeah.
Yes? Wait, what? What? I think we need to do this here. Yeah, I didn't run the ID, sorry. Queen is higher than Elizabeth. Which model are you using? Same or the previous one? Because wait, I run
it twice.
I am running it with this model. But in your script, that's the last model in the script. So I click this once again. This one I clicked it again so that this model is loaded. So if you haven't clicked that, you are using this one. You can do this and see which model is I thought it said, but I don't know.
Which words are you comparing?
Come again?
Which words are you comparing?
We are comparing these words.
No, I mean the ones you are arguing about. Is it Elizabeth and Queen?
So in your colleague's instance, Elizabeth was higher than Queen. But I think that has to do with using the other model than this. So in our model, which I still say that it's good, Queen still remains higher. So it's the most likely outcome out of this mathematical thing we tried. So from king, we removed whatever man semantically means for the model. We added woman and whatever that semantically means for the model. And that made it return a vector that is closer to the vector of queen. Is that clear? Isn't that nice? And you can do this mathematically. I think it's insane. I mean, you should appreciate this. I mean, you don't have to.
We do, but we cannot show it.
You don't have to. But yeah.
I tried for Turkish, but it didn't work.
So, I have this exercise for you. I don't think we have enough time. I mean, we have about 5 minutes and then we're going to need to go to lunch. But you're welcome in the last 5 minutes to try with, the capitals and countries example. So Paris minus France plus Italy should give us... Speak up.
Rome?
Yes. Should give us Rome. Or with something in Turkish. That's the one I tried and it worked. This one worked, but you can try, because I think the word king is not really translating very well in Turkish.
No, I tried a name of a Turkish queen, but there's a U letter.
Okay.
doesn't work very well.
I put sultana and it
I was sure it's multilingual. Come again, what did you say, sorry?
I said I included sultana, which is usually for a Turkish princess, and it's classified as such.
I'm pretty sure it's multilingual, but maybe I'm wrong. Are you certain?
No.
Okay.
I'm just a question.
I mean,
what is the model again?
Mini LM L6 V2.
Should be multilingual. Should be multilingual.
I'm pretty confident. I'll check, but I'm pretty confident. But anyway, please try with other Turkish words and tell me what happened. So we can continue on this afterwards, because you have about 3 minutes. So you're welcome to use others. So go back here to this list and replace it with your Turkish words or the other example that you want. Then put the ones here. In the meantime, is there someone with a question?
Is there a chance like to print the vector with an array vector that we set?
Can you repeat that? Sorry.
Is there something that we have an embedding? Can we like just print the output if we don't know, or just if there's something like that? I don't know.
To print the embedding.
Yani we have an array vector, right? That's an embedding, a full embedding, right?
Yeah, it's a 384 thing.
That represents a word.
That represents this mathematical thing that we did. It doesn't represent a word.
Yeah,
it represents this minus this plus this.
Yeah, but,
it's not a word.
Yeah, that's awesome.
But we take this now and we compare it with all the words, the embeddings of all the words, to see which one is closest. And queen happens to be, which is what we expect to come. But I mean, yeah.
By the way, I tried being sarcastic with it and I didn't understand.
It didn't? Fuck. So what was the example?
So I wrote, you should have a, one second.
Like
you
in
should
this?
look happy with that grumpy face, and it thought it is, it has a very similar meaning to, that is a very happy person. So the first sentence was, you sure look happy with that grumpy face. And the second sentence is, that is a very happy person, and I thought it's similar.
Yeah, but I mean, I wouldn't call that a failure, a false negative necessarily, because in my eyes, it has to do with like these are super short sentences.
Yeah.
It's not very easy to compare. It's not very fair. It's a hard task, right? Yeah. So try maybe a longer sentence, still with sarcasm. So tell me the sentence again.
You sure look happy with that grumpy face.
You shouldn't.
You sure look happy with that. You sure. You sure look happy with that grumpy
so
face.
you are happy despite having a grumpy face.
Yeah.
Like no. I mean, why are you grumpy basically?
Yeah.
Right? Yeah. Yeah. It's a difficult bar you're setting, but thanks for trying that. Yeah, that was good. I urge you to try a little more, maybe with longer one with context. Yeah. And there are models that can, because I understand you're interested a bit more in social media, short form. So there are models that can read emoticons as well.
Read what?
Emojis. Emoticons. Yeah. Which are really, really important for social media and, well, Twitter and other ones as well. Anybody tried this already? Has some results they want to share? If not, I think we should stop now and go for lunch. And we can continue later with this exercise as well. Like, don't worry about it. We can continue from where we left off. So, welcome back. We have an important decision to make. We have about 3.5 hours ahead of us. Then we go to dinner, and then you get the last to my understanding, the last chance you have to work on your projects, because because tomorrow you're not going to have that chance. I think you're going to dinner and it's the closing ceremony or something. So today is your last day to work on your projects, basically. So I'm thinking two things. Also, I was told that we should today and tomorrow end both the morning session and the afternoon session a little earlier, so that you get a chance to go to the restaurant on time, because the campus is full of people from other summer schools, etc. So sorry, I didn't know that in the morning, but it wasn't that bad, I think. But maybe for the dinner it's going to be bad, so we anyway have to end a little sooner. So let's see, we have, as I said, 3.5 hours ahead of us. My recommendation is that we spend 2 hours on this stuff, and in the last hour you use it to work on your projects with us here. Then we go for dinner and then come back and you continue working on your projects. How does that sound to everybody? Yeah? Anybody has a big objection? Okay, so let's do that. So let's continue. Before we continue, remind me, what's your name? Omer. Would you like to show your colleagues this really nice finding that you had with the German word? No?
Okay, no problem.
I mean, if you're okay with that.
Yeah, okay.
Yeah. So I think we should spend at least 5 more minutes on you guys trying to work on this exercise 0. And I remember some of you were working before on it and you stopped it. I think you should continue working on it a little bit just to play around with this. I mean, again, this is a toy example, but it's useful in understanding, and then we'll move to the serious stuff. But while we were doing this, Omer found something really interesting. Would you care to come up? I mean, just so that we show with your laptop. I mean, you can tell us the words you used, and I'll use them. Yeah.
Instead of king, I just used the word doctor.
Okay.
Doctor, and the queen, for the queen I used nurse. And
Man, woman, the rest,
man,
right?
woman, and the rest.
So, yeah, and let's change it here. Sorry. So I'm running this again, but now we are taking the word doctor and we are removing the embedding for man and adding the embedding for woman. What is the word that you expect the outcome embedding to be closer to? Man.
Yeah.
No. We have doctor. So instead of this, we are doing doctor minus man plus woman.
You get nurse.
Okay, why do you think we should get nurse here? So actually, when Omer run it, he got nurse back as the most common. I mean, okay, remember that we are also limiting the options, right? We have Prince, Elizabeth, Victoria. These are words that don't really correlate with doctor. But we should be aware of these biases. In this case, we can only think of nurse as a female medical specialist, right? Even though there are male nurses as well and female doctors as well. And then another super interesting point on top of that was that Omer said that in other languages like German, there are gendered words for professions. So there's the word for doctor for man, which is what? Okay. And the so there's a man word for doctor and a female word for doctor as well. So in some languages, this potential bias is in the way we use the words, and in some other languages, this bias is not there by default, but by how the language is structured, right? So this is something really important to have in mind when we're talking about the biases of these models as well, right? Thank you again, Omer, for that. So please spend the next 5-10 minutes those that have, I mean, is there someone still working on this? Okay, so please, let's spend the next 5-10 minutes on this. Maybe five should be enough. And you can do exercise 0. Has anybody already worked on one of these and got some interesting example?
It wasn't interesting because it was.
What did you try?
I tried Ankara minus Turkey plus
Okay.
USA.
And you got what?
It got Washington and then capital DC, capital
Okay.
Seattle, Virginia.
Okay, cool. As expected. Yeah, okay. Anybody else? Okay, I'll just give these 5 minutes and then we continue for the rest of with the rest of the script. Is that okay? Look, we don't have super much time.
Yes, just quickly.
Yeah. So I would skip this part for now. Like don't worry about it. So the important thing we're doing is this. So anyway, let's go a bit up. These are the libraries we're using. And from the sentence transformer library, this is where we download a model in our machine. The first time we run this, the model will download it. So it takes some time. So for 4 minutes in your case. Every time you use it then, it should be in the memory already and shouldn't take this much time to load. But remember that we are in Google Colab, so every time you also refresh it, you lose everything in memory, so probably will take the same time. So once you have the model in, let's say you have 2 sentences, this one and this one. Now we can calculate an embedding for this sentence and an embedding for this sentence with this function here. We got the model from here, and we get the .encode function. Encode. So we are encoding the text into numbers, into an embedding. And in here, in this parentheses, we introduce a list here. So square bracket, comma, square bracket means it's a list. And it's a list of 2 sentences, sentence 1 and sentence 2. This list could be as long as we wanted. You could put 100 sentences here, 1,000, okay? We're just putting 2.
When it's that long, do you put like integers like to the nth degree or whatnot, or like does the coder have to input all of the sentences?
Oh, yeah. It will just take time. It's not a big thing. So it takes 2 seconds for 2 sentences. It will take 100 seconds for 100 sentences. So now it calculated embeddings, and if we check the embeddings, the first element in the embeddings, so the embedding for sentence 1, this is how it looks like. Sorry. I mean, it hides many, but it's a 384 dimension embedding. So these are numbers 384. Okay. So in order for us to compare semantically this and this sentence, we want to compare the distance between the 2 embeddings. So the embedding for this sentence and the embedding for this sentence. To do that, we calculate cosine similarity, as I said. And that comes from this package, where we imported cosine similarity. And we simply do cosine similarity, parentheses, parentheses, dot item, so that we get the final thing back. And inside these parentheses, these 2 parentheses, again we put a list of the embeddings that we care for. So cosine similarity between embeddings 0, so it's this, embedding for sentence 1, and embeddings 1, which is the embedding for sentence 2. Does that make sense? And we get this value. By the way, I'm also using round here, so I'm wrapping all of this inside a round parenthesis with 3 digits. So we get 0, 7, 4, 2. So closer to 1 means similar, closer to 0 means not very similar, okay? And this is very similar. It means that these 2 sentences are very similar. You can also change the model if you want. You're welcome to. But don't do it now, it doesn't matter.
With that model, by the way, with the Queen Elizabeth answer, with that model, Elizabeth came second, but with the previous model, it came like 4th or something.
Yeah. I mean, again, different models can bring different answers. So this is just an example of another model. It doesn't seem that it's a good one or better one, but this is definitely a good one. Okay, the one we are using is definitely a good one. And here we do the same with multiple sentences. Imagine you had 4 sentences here, and we run again model and code, and we feed this list of sentences in here, okay? And we create a new object called similarities, and we calculate cosine similarity between all the embeddings and against all the embeddings. So one by one, the embedding for this against this sentence, and so on and so forth. And you get this matrix, which is 1 is this versus this. This one is this versus this. This one is this versus this. And this one is this versus that. And then for the second sentence again, one by one by one. Okay. So this diagonal is everything with itself, and we don't care about this. So we replace it with -1 here, because we don't care about that. And then NP argument max returns the highest value that it finds in here, and the highest value is this. Yeah. And then we just simply print the 2 most similar sentences are, this is a happy person, this is a very happy person, as expected. This makes sense? This is what you should care for, yeah. Don't worry about this. All right. You had a chance to finish as well? Good. Anybody has something they want to share about their example? If it worked, didn't work, as expected, not as expected?
I've actually tried multiple languages.
Okay.
So I took king minus erkek.
Okay.
Plus madame, and it gave me queen.
Cool.
Yeah.
So at the same time, multiple languages in the same text. Cool, and it worked. Okay. Yeah. But what other words were in the list?
I had queen in English and Turkish.
Bravo.
And
it went with the English one.
Yeah, with the English one.
Interesting. Okay.
Like I just give him some names like John.
Okay.
Like Sally, and just ruin the things that didn't figure out.
Well, because you're very challenging. You're doing things that are very challenging for the model. Okay, but you both, I mean. Again, names are super common in this case. John and Sally, they are, yeah.
Mostly known as for instance, male name. This is why.
So it would be interesting though to see some, imagine in the previous paper that we discussed with the 100 books across the 100 years. Imagine if we tried to connect affluence with name choices of babies. So I guess in the 1900s, people would name their kids in one way if they came from a higher class. And maybe nowadays this reversed. Because I don't know if you know this, but there is a clear string in social science that checks how people name their babies and their seasonality to it. So every other decade, what names are cool and in fashion, come like fashion itself. So it makes circles. So people were using some names at some point, and then they made a circle. So there is seasonality to that as well. But the names you chose are very, very simple, I think. So it's kind of hard for the model. Anything else?
I did a silly one. From Turkish, I extracted men and then included women.
Okay.
And I added some other nationalities, French,
okay.
Iranian, American, and British, and French was the most it was the most similar.
What was the most similar?
French.
French. Okay. It's kind of weird. Yeah. But what are the other words in the list that it could pick from?
French, Iranian, British, American, and other like random words. Princess, bank, president.
Yeah. But again, yeah. But it's okay. It's interesting. Yeah. All right. So guys, let's continue. Now let's try to calculate embeddings from real data. All right. We have the AG News data set. So again, remember to return to the faster Lytle model because the other one is going to take long. So if you don't have, run this again. And let's calculate embeddings directly from the text column we have in the newspaper data. So sorry about that. So if we look at newspaper data, we have this text column that we created, right? So now when we calculate the embeddings, we're gonna fit that column inside the model, all right? We're gonna fit that entire column. And to do that, we first transform that column to a list. So if we run this separately, if we run this separately like this and inspect what texts look like, now it's just a list of text. So imagine it's a list of sentences, a list of article bodies and titles together, okay? So this is now what we're gonna feed into the model to calculate embeddings on. Remember before we did that exact thing in this example case where we calculated embeddings for all the sentences, right? These 4 sentences in this case. Now we're making this list 3,000 elements long based on the data frame that we had, which is 3,000 rows. Does this make sense? Is there someone that this does make sense for? Okay. Okay, good. So in this example, you didn't get it. Yeah. So in this example, we calculated embeddings for every one of these sentences, right? And in order to do that, we created this list. Can you see these square brackets here? And then there is quote, quote, comma. Quote, quote, comma. So that means that within the square brackets, each of this element, it's an element that belongs to a list. So this is, sentences is a list element. So then when we go to create the embeddings object with model, which is the model we have, right? Model.encode, it's the function that we call to calculate embeddings. In here, in the parentheses, we just fed this list that we have here. And this list, in this case, was 4 sentences long. Now we want to feed it all the rows of our data set, the text column that we created, right? Those are 3,000 sentences, 3,000 articles, okay? And in order to do that, in order to do that, if you look at newspaper data, there is the column here, text, and we are transforming that column. So newspaper data, square bracket text, so that's the text column of newspaper data. We transform it to list. So now this is a list of 3,000 sentences in it, okay? And that's what we're gonna feed in the model encode, that encode thing now. Does this make sense?
Yeah.
Really? Good. Is there someone that this doesn't make sense to yet? It's super okay to say it does make sense to me. 3, 2, 1, okay. That was your last chance. So we transform it, we get the text, we show it. So now, yeah, it was already here. So now we create an embeddings object again with model.encode. And inside, we feed the word texts, or the object called text, which is the list. And we have this opportunity to use this argument called batch size. So the model will try to do things in batches. So not one by one all the time, but just every batch size in every batch. So that increases the performance a little bit and cuts down time. And we also have this show progress bar through, so that we get this progress bar and we wait. So while I run this, it will take around a minute. Has anybody run this already? Okay, some people are going ahead. I know that. Please bear with everyone. Again, this takes roughly around a minute. How long did it take for everyone? Anybody got way higher than that? Around 1 minute for 3,000 sentences, right? Calculating an embedding for 3,000 sentences, which are not super long, but they are 3,000. So if we had a longer data set, it would take much, much longer. If we had a GPU, we could do it parallel. If we had a better CPU, we could do it parallel. So many options here, but this is like the straightforward one. I think it's going very slow in my case now.
If you had a bigger data, would you increase the batch size? Is it batch size like dividing into sessions?
So it's dividing 3,000 with 64. So it's...
If you had a bigger data, you would divide it with more numbers.
Yeah, I would increase the batch size. Yeah.
Here is showing error.
What error?
It says track back motion. Maybe because the model is different.
Can you go down to the error? So you don't have the text column in your data frame. Go up. Go up.
Oh, okay, so I should activate another one.
Yeah, you need to create the text column. Remember, the text column is the combination of the title and the body together into a new column. We did it above. Okay, so it says a minute, but in my eyes, it's 1 minute 54. So around 2 minutes, basically, okay? And if you look at the shape of this embeddings object that we created, it's 3,000 embeddings of 384 dimensions each, like we were doing all day today, all right? Obviously, when you calculate dimensions, embeddings for thousands of documents, it's not good practice to recalculate the embeddings every time, right? It's much more efficient to calculate once and store these embeddings in memory, so that then when you open your session, you just read the file with the embeddings in it and you continue working from that, okay? So here you have this np from numpy.save, and I create this file which is a .npy, which is a numpy file. So arrays of numbers are stored in an efficient manner, and the embeddings object, and I'm saving it. And then with this line you can also load it. So remember to do that and download the file locally, not just inside Colab. So if I run this and save and I go to files, I will get my my embeddings file is here. But if I close my Colab and refresh it, these files are gone, right? So remember, now you have to go here and download this file locally to your machine, and that's where it stays then to continue working on it. Just don't forget about this, because you're gonna have to recalculate everything. So let's say we want to see what the first article is about, and like sort of its embedding. So here we see that the article is Oracle to drop PeopleSoft, suit if tender fails, Oracle Corp notified Delaware's blah blah blah, the drop blah blah blah. It's an article about business and this company called PeopleSoft, and this is the embedding, but only the first 10 numbers, so it has an embedding. So here in this cell next, we are choosing two completely random articles. Article A is the 2000 article in our data, and article B is the 2002 article in our data, okay? And we are calculating the similarity between the two with the script here. So if you run it, there's nothing complicated here. There are just print sentences. Everything happens like before. Cosine similarity between article A and the embedding of article B, okay? We've done this already 5 times today, so don't worry about it too much. So I'm just using article 2000 and article 2002, and this just prints it. So article A is baseball today, AP, whatever happened in this game, and article B, NASA reviews mix-up that doomed capsule. So two completely unrelated articles. One is about sports and one is about science, I guess. And the cosine similarity is very low, 0.059, okay? So now please change these values here and do your own thing, play around with your own values, and see if you get common articles with high cosine similarity or articles about different with low similarity. or if you get something that is unexpected. Try to find two articles that are clearly similar. If anyone is having issues, technical issues, now is the time for me to help them. Did you manage?
When I run it, the embedding, it gives me two relation.
Okay.
Like I was running the similar thing,
Yeah.
and I wrote that one. Because this one, it wasn't here. I wrote it again.
Yeah.
So is
Oh,
it
you wrote
also
this?
relevant?
You run this?
Yes. But I can write if I run it again because
You should, because what?
no. I think I ran this after I ran this. Shall I run it before that one?
Look, everything looks fine, but yeah, there are 47 batches, and every batch has 64, so it should be 3,000. So just give it a minute to run this, and then once this is done, run this again. This should be then 3,000. I don't know what happened here.
Okay.
I guess you didn't run this, and it was
I ran it maybe.
it was this one. So the last time you did embeddings was only 2 things, but don't worry about it. Don't worry about it. It will be fine now after this. Are you following this?
Yes, yes.
Good. Anybody found something that doesn't make sense? Or like 2 similar sentences? That they are completely opposite directions, even more different than different. If that makes sense, yeah. Where did you get a 0 minus score? With what values here? Can you tell me?
1,789.
Is that a specific? Is it a special number for you? Okay.
I was just pressing that.
Don't worry.
79, not 89. And 1,580.
18.
80.
No. While I was waiting and walked there, the whole session disconnected. So look, no data here. All the data is gone. So I need to import the libraries again. Terrible stuff. So just give me 5 minutes, like 2 minutes to rerun some of this. Sorry about that.
What is it about?
Come again?
What is it about? The Wi-Fi connection?
Maybe. I lost connection to the Colab notebook, so my connection with Google servers was interrupted and it had to be restarted. So I don't think it has to do with the network, but I don't know, maybe. It would have been the same for everyone, I guess. Sorry, just a minute. Well, maybe 2. So look, now I'm downloading the model again once more. Did it work, by the way? Was it 3000? Sorry about this delay, guys. Is there any question while we're waiting, maybe?
So I have a question about the transforming the text into list. When we had a finite list, like small size, we could see the list, right? But in this case, the list did not appear, even though we know the shape.
You think that's problematic?
No, I don't think it's problematic. I'm just curious.
So let's say we go back to your project, which is the Ghanaian parliamentary speeches. So you have 20 years of parliamentary speeches. So it's going to be, I don't know, hundreds of thousands of rows of people speaking in parliament. What are you going to do? Read all of those? Like you can inspect chunks of those, but you cannot go through all of them. So you just feed it without having looked at all of them. That's standard practice when we're working with so much data. Like there's no time for you.
Set it that way so that, and how, if you set it that way, how do I set it? Or it is just normal?
So in this line here, so before I run the model.encode, before I calculate the embeddings, I am transforming the newspaper data text column, I'm transforming it into a list. When I do that, I get an object that looks like this. It's just that instead of only 4 sentences, it has however many rows there were in the data frame at that time. If in your data frame there are 100,000, I'm going to get a list with 100,000 sentences in it. That line does that. Okay. Actually, I'm going to save this and I'm going to download it. So next time I don't have to recalculate. Sounds like a good thing to do. So it was 1789. Let's just check it very quickly. So finish line, November 1, Andrea Gassi lost the Stockholm Open final. I think Andrea Gassi was a tennis player. To Thomas Johansson, who won 3-6, blah, blah, to capture this tournament for the second time. Walmart misses comp sales target, November same store sales. So one is about sports, the other one is about finance, economy. So it's understandable that similarity is also negative, right? These are completely different things. They shouldn't be nowhere near each other in the geometrical space that we are creating. Okay? Anybody else has some rows that they would like to show to people because they're interesting?
Yeah, I also have negative sign.
Can you tell me?
They are, one is about business, one is about world. So this kind of classification.
Can you tell me the numbers?
Yes. 1845 and then 1800.
Jackpot at 30,000 feet, about Ryanair, might introduce in-flight gaming, good stuff. Kalam to leave for Abu Dhabi to offer condolences, I don't know who that is. President Abdul Kalam.
No, that's.
Do you know who it is?
President of India.
India, wow. So again, one world, one business, and they are completely indifferent. They're completely different from each other, as expected and as it should be. Anybody with two very similar sentences?
For me, like, it's not negative, it was positive, 0.16.
Okay. Anybody with a cosine similarity of over 0.4, 0.5?
0.9.
Wow, can you tell us which one?
52 and 1,432.
52?
Yeah, 52
and
1,432.
Wow. Okay, Yahoo profit, Yahoo's profit. So basically this is the same article, eh? Probably in a different... Come again?
Sometimes in capital letters, profit
Yahoo's profit and
No, I mean, when I say that the same article, I mean, it's about the exact same thing with the exact framing, but just in two different media websites, yeah. But they are covering the exact same story, I assume. Come again?
I said, what a coincidence.
Not really.
That he gets these two.
Yeah, that's a good, yeah, that was a coincidence, yeah.
I wrote a script that goes over the...
Ooh, fancy. Would you like to tell us what you did?
So it's a for loop that goes over the 1 to 3,000, and
Okay.
then another for an inside for loop that goes from the above number to 3,000, the max number of articles. So basically, it compares every number
To every number?
of the other article until it finds a specific similarity, a threshold that I set to 0.9.
Okay, good, excellent. Basically, this is what we're going to do next, but without a for loop, which is great.
Yeah, it took a long time.
Exactly. So what we are doing now when we're working with embeddings is working with NumPy arrays. So NumPy is a library in Python that allows us to work with numbers so long like these, like matrices and vectors, in a much more efficient way than a for loop that compares one number to its other. So for loop is not efficient. It goes sequentially in the CPU, every request one after another. But with NumPy, you can do this in parallel and much faster. Okay, it's really efficient. So we are working with article 2000 again, which was this Baseball Today thing, and we are trying. Actually, let's do what you did. So article 52. And we are trying to find the article that is the most similar to this article, right? Out of our entire collection, okay? So we create an object called scores, and we do cosine similarity again. And now we do embeddings, and embeddings of that row, the embedding of that row versus all embeddings. Okay, so instead of a for loop, we just put cosine similarity right away. This is a vectorized manner of working in Python, and it's much faster. So this takes 0 seconds. It was instantaneous. And now we can print the results. So now what this did is it created a similarity column that compared the embedding of our one sentence with every embedding in our data frame and got a cosine similarity. So here, this column, the similarity column here, has the score of how similar is the embedding of our sentence, number 52, with every row there and its embedding. Does that make sense? So if I go down to row 52, where our row was, the similarity should be 1, right? Because it's the sentence itself. I can remove that query article itself because I don't want that. And then we just sort by similarity and keep the top 5. So we reorder the data frame by the similarity index, so the highest values go on top, and we get the top 5 with head 5. And these are the 5 top sentences, and actually 1432 is the one with the highest similarity. So exactly what you did in a little bit faster way.
Can I set a threshold for this?
Yes, so when we created this result, so now you have a similarity column here. So now with the similarity column, this is a numerical column, right? So you can do whatever you want. You can say, remove everything that's below 0.3, keep only anything that's above 0.5, whatever you want. But you would do it in this step here. Good? Does this make sense for everyone? Well, is there anyone that this doesn't make sense to?
Come again, which step do you use to set the threshold?
We didn't do it.
Oh, okay.
But are you with me unto this point? Like, do you have a similarity column in your data? So this is a numeric similarity. What am I saying? A numerical column. So here you can filter. So let's generate with AI. So help me filter rows that are above 0.5 in the similarity column. Are you following this? So this creates a new data frame called high similarity results, and from the results it goes and keeps only those that in the similarity column are more than 0.5. I mean, it's extremely fast, so you don't really have to do that, because if you're just looking for the top one, you don't really have to do that. But if you're looking for, okay, you're right, I mean, with head, this was just to show this, but anyway, yeah, you can do this, and now we have only only 5 rows again that are above 0.5. Yeah, happens to be that only 5 sentences were similar to this one with a score over 0.5. If we lower this a bit to 0.3, wait, what?
Maybe it only shows the top one.
No, I think we worked on a different object. So there are 1, 2, 3, 4, 5, 6, 7 rows that have that score. That's over 0.5. And if we go to 0.3, there are 130 rows that are above 0.3. Does this make sense for everyone? Please tell me if this doesn't make sense for everyone, please.
Is there a cutoff point to count it as like similar or not? 0.5 maybe.
Actually, okay, 0.5 is a nice score. Everything as above 0.5, you can confidently say that it's very similar. Everything above 0.6 is very, very similar, especially when you're doing more complex stuff that is a bit difficult to find. But setting the threshold is really a matter of inspecting similarities and seeing what happens. Normally what we do is we create a distribution of similarities, and we see where the majority of the text lies, of the cosine similarities lie, and we draw a line that we are comfortable with being over and below, and we also check those that are over the line and behind the line, and to offer some validation of this. Okay. So that was the Curie article 52, and the top the top rows that are I mean, sorry. Yeah, the nearest article, but we're doing it the other way around. Let's keep this. So you're welcome to change the Curie row in the next 5 minutes and play around with this and see if it works, and if you're getting the results as an exercise. Just giving you 5 minutes. This is really not that important as well. you can check if the nearest articles that you get are from the same topic or not. Because maybe sometimes they are a similar sentence, maybe talking about something similar, but they are from completely different topics. Because we are talking about, I don't know, the president visiting the press, but on the one hand, the international category in the newspaper is covering it because they want to cover the president meeting the press, but then also the internal the national, the one about national politics section also covers the president being there from its own perspective, right? So, of course.
For the sentence embedding, is it happens by taking every embedding of every token and then averaging the sum, or comes another
No.
way?
It's directly with all the words in there. So it's an embedding for all the words, the order that they are in, the punctuation, everything matters to get that embedding. So it's not word by word. It's an embedding for all the thing that you're feeding it. So if I say, Yani taught a class today, and if I say, Yani today taught a class, these are going to be two different embeddings. Very, very similar, but different because just the word order was different. So the embedding is for the entire thing as it's fed.
It's hard to understand how this works, right?
Is it easy to understand how the embedding is calculated for one word?
Yeah.
It is.
No, not easy, but you get the idea that every word strand code have one embedding. So that's what I understand.
Yeah.
But how it's like connect the words, different words, that's what.
So you should only think about it in the same way, in the following way. For the embedding model, the model that we are asking to create an embedding, all it needs is an object. It doesn't care how long it is, what it contains. It can be audio, as I told you, can be an image, as I told you, and it can be text. A text can be 1 word long, or can be 1,000 word long, or 1,000,000 word long. So it doesn't care if it's 1 word. So it is doing the exact same effort for 1 word or for, exact same process, not effort but process. Yeah. So a word is a very small sentence of only 1 word, but it's still sort of a sentence, right?
For example, if I write anything, not a thing, some characters, what's gonna create?
It's gonna create a gibberish character based on how many times it saw that gibberish pattern in the text. So if you do something like that, yeah. If it had seen this before, it's gonna try to work with the data that it had seen before for this, but it will create an embedding. Will this be useful for you? I don't know. Maybe in the embedding space, the geometric thing that we talked about, maybe it's gonna be a very outlier somewhere completely far from everything, because it's really not common in the text. That would be a good finding actually, if it happens. If it's very close, something else actually wouldn't be a good finding. Yeah. Anybody would like to report something about this exercise?
I think that when I run the similarity, I get maybe about 4 or 5 of them showing, right? Not everything will show. Then I try to filter for similar ones with a threshold, and it uses only what is showing me on the screen. Let's say 5 of them and then 1.
Yeah, so you need to run this filter. Can everybody see the screen or not really? Anybody having a difficulty seeing the screen?
He said he does.
Thank you. No, not so much. Is this better? Is this better?
Yeah.
I mean, nothing to be ashamed of. I mean, you're in a workshop spending 6 hours of your life here. You should be able to see this and take advantage of this. So don't worry about it. Is this better?
Yeah, it's okay.
Cool. So this line where you filter for you set the threshold should come just after you calculated the results. If you run it after you run this block, it's going to show you only the 5 because this focuses only on the 5. So it replaces everything with just the 5. So no matter what threshold you set, it's still only the 5. So they are already above 0.5. So it's always going to be these ones. So remember to do this right after you calculated the results for the first time. Okay, with regards to the exercise, is there anyone that wants to report something? You don't have to. Okay. So now let's do this and then take a break, okay? Everybody okay with me, on board with me on this one? Okay. So we compared one of the sentences in our data frame with all the sentences in the data frame, right? But let's say we have a list of documents and we want to compare all the sentences in our data frame with our own concept and our own definition of the concept, right? Let's say you want only the articles that are about the economic crisis, some economic crisis, only about the war in Ukraine. So what we have is categories of articles: world, sports, tech, and no other thing. So how would we filter or search for articles that are closer to the topic of the war on Ukraine, let's say, in a data set like this? So we would create something like a search text that we can put in whatever we want. It's our definition, so you can play around with this. For now, let's work on a football team wins an important match. This is the thing we're trying to search articles for. So we want to get all the articles that are about football and teams winning in football, okay? So we said that, we defined that. Obviously, guys, the way we define this matters, right? What we put here in words matters because it's going to change the embedding. So what we do is we define this sentence and we ask model.encode to create an embedding for that sentence. And then similarly to what we've been doing all day long, we'll get that embedding and calculate cosine similarities with all our data frame again, okay? Line by line. So you can run this. And now we create this object called search scores, which is cosine similarity. Same as we did before. The search embedding, the embedding of our sentence, versus all the embeddings in the data frame. Cosine similarity for all of them. Make sense?
We are intervening in the data.
Come again?
We are making an intervention into data.
What do you mean?
We are, like, there is the data, we are making an intervention, like we are comparing our intervention with all the existing data.
Yeah, so it's our definition of whatever it is that we're trying to search. You can make this as long, as small as you want. And we are taking its embedding, calculating an embedding for it, and taking that embedding and calculating its similarity with all the embeddings in our data frame, because we want to get those that are more similar. Yes?
The text, the research phrase
yes.
we entered, it's almost like a sentence and
yeah.
the verb and everything.
Yeah.
How about if I search something on misogyny, for instance?
Yeah.
Can I just use one single word?
You can do keywords if you want. You can play around, separated by comma. You can try that, yeah. It will create an embedding that represents this list of keywords, and then it will try. I don't know if it's going to work or not, but it's something you can try. There is no good.
It doesn't have to be a verb or.
No. It doesn't have to be a sentence like this. Maybe a sentence is a bit similar. Is a bit easier to create. So if I create a sentence that sounds like an article, on average I'm going to get higher similarity scores with a data set that is article titles, right? If I create a list of keywords, the average similarity of comparing list of keywords with article titles is going to be lower. That's not a problem because it's a matter of comparison. It's a comparative thing. You don't care about the average. What you care is the relative to each other. You want the highest scoring even if overall we are lower. So yes, you can do a keyword list as well. And we get search scores. And search scores, as expected, it's 3,000 long. Now we are, as before, creating a copy of this data set, and we are creating a new column called similarity. And here it's our data set again with 3,000 rows and the similarity column, but of our created sentence, not a sentence of the data set like we did before. So this is now our defined concept against all the text rows here in the data frame, one by one.
Since the model cannot differentiate between questions and concepts, is it common that if I search with a question, does it realize or does it help me with giving me answers to that question, or it won't be?
So this is not a chat model, like asking an LLM a question and waiting for an answer to come up to be generated. So this is more like compare this to this, give me a score. Compare this to that, give me a score. This to that, give me a score. This to that, give me a score. So it's not really. I mean, you can put a question here, and what it will do is it won't try anything. It will give you the similarity scores that look like questions more than statements. So this is a statement. So you might get a bit more similarity with questions than statements. So if you are, let's say you are looking for articles that have questions in the title. So it's the journalist asking a question towards someone. Maybe framing it as a question might help you find those more. But then you can also go for looking for a question mark in the title, and maybe that's easier.
I thought the answers have similar embeddings to their question. So if I ask a question, it will output a similar answer.
No. And also, guys, this semantic comparison is more about the content of this sentence, not so much its structure. It's more about what is it talking about, right? It is about football, a team in football winning some match that was important. Doesn't really matter if I ask it as a question. It shouldn't matter actually so much, yeah. Is someone not understanding this thing that we just did? Now is your chance. 3, 2, 1, go. All right. Either we are doing a great job or you're also very tired. So if I want to get now the most similar sentences to my concept, I can do it with the 8 most, like we did before. You can also filter as we did before. You can do all of the things that we did before. So if I do the 8 top, we can see that the Kansas City Chiefs showing poise well beyond his years, blah, blah, blah. I guess this team won. Biggest game of the year, Man United versus Arsenal, the biggest game of the blah, blah, blah. Donovan McNabb, 356 yards. Georgia versus Auburn, a game with everything. So, I mean, this is confounding a little bit the football we have in Europe and we call football, and the football they have in the States, which is the one they play with the hands instead of the feet, but still called football. Yeah, I mean, it's again common joke. Anyway, I mean, we are getting articles that are about teams playing football, be it one football or the other, right? if we were to say an American football team wins an important match, let's try that. I'm gonna keep this open for now. Wait, let's do the foremost. Okay, and run this again. An American football team, doing the scores, doing the search results. So there was this biggest game of the year here, which is about European football, Man United versus Arsenal, that now is not in the list anymore. So I guess the similarity went way down. So what this tells you is that what we put in here obviously matters, right? So the way we define the concept is important. And what I would urge you to do is, again, in hopes that you convince some reviewer that is reading your method section that this worked, is that you try various combinations of your definition and see if the result is robust. Because if minor changes make have completely large impact to your findings, then your finding is not robust. It's not good enough. Does that make sense? Let's take a break and come back for another hour of embeddings. Is there a question maybe before we do? Okay, cool. So we reconvene at 20 past, is that okay? Okay, but let's be in the room at 20 past so that we can start, because I don't think we have too much time, given that in the last hour we're gonna work on the projects, okay?